Musím restartovat OSB. Proč to je tak pomalu? Včera to jelo. Jo.
No ten stream jsme vyloženě vyzkoušeli.
No to ne, no.
To jsme měli vyzkoušet, no. Teďka jsme tam měli.
Job also in general through the last 3 months. Thanks for the sponsors, Red Hat, who donated the time of the local team, myself, Karen, and Arma, who is a gold sponsor and basically is providing the food and the venue. Nutanix bought the t-shirts. Next time, don't make them arrive last Friday, because I was scared that there wouldn't be t-shirts. And especially thanks to our speakers and attendees for trusting the new organization of KVM Forum. So what's next? Again, I really would like it to go back to the sizes that we had to pre-COVID. I think the top was 320, something like that, attendees. We can do it. Because of the organization, we need a strong local team, and that's why probably we'll stay in Europe. But again, if you have proposals to have KVM Forum elsewhere, just contact the program committee and we can talk about where it could be. Those are like 3 random cities, but it's not a given that it will be there. Like we could have it in Fosdem so that people can travel to 2 conferences at once. We could have it in Milan, which I personally would not mind. Or maybe, I don't know, there's a lot of people from ARM and Google in Cambridge, so that could also be an idea, just like this year we have lots of people from Brno. So just if you want to help for local organization, or maybe your company could provide travel sponsorship, or even if your company would like to donate time to be in the program committee, we are open to all sort of changes, and in the interest of making this a real community conference that is felt by everybody in the KVM community. And also, new for this year, we are going to have a KVM micro conference at Plumbers. We proposed it not long ago, but it's already been approved by the Plumbers organizers. So for those that will be able to travel in November to Virginia, see you there. And let's go on with the other keynotes and the talks after that. Thank you.
Okay, let's quickly get started. Quick introduction for those that don't know me. My name's Alex Benet. I'm the virtualization and emulation tech lead at Linaro. You'll find me on the Cremu IRC channel as ST Squad. I've got my fingers in a number of pies, including testing, bits of TCG, plugins, and the GDB stub. And as of this year, I'll have been working on QEMU for about 10 years. So this is the 4th time I've given this talk, and I'm a little worried that I was getting a bit stale, and I wanted to try and keep it fresh. So I thought I'd ask the internet about what they wanted in this talk, because we all know nothing goes wrong if you ask social media for people's opinions. And I thought maybe if I somehow mention AI, I'd also keep the talk relevant. So I did a quick poll. It was on Mastodon, so not that many people saw it. But as you can see the results, most people are hot for data visualizations. Absolutely nobody wants any league tables, which is slightly disappointing because all of my previous talks have had league tables in them. There was a bit of a desire for editorial content, so I'm going to try and add some hot takes and also give a bit of a breakdown of what our contributor base looks like. So let's look at the last year of development. I've done this for the whole year, mainly because I was too lazy to change the scripts. So this does include a little bit of the time from before the last KVM Forum. So these are the old sort of graphs that I used to do. You know, pie chart, terrible way of trying to represent the sort of changes that are going on in the code base. So I did a lot of looking around to see if I could come up with some better visualizations. I realized the first thing though we need to do is try and quantify the size of QEMU as a whole. So we have this. This is a tree map. So in this tree map, the size of each rectangle is basically proportional to the lines of code. So you can see roughly about a third of QEMU is all our hardware emulation, and then we've got various bits for the target specific. Tests a pleasingly large chunk of the code base, and then it all starts getting smaller as we go into the smaller bits and pieces here. I must admit, I left off the PC BIOS directory with all the ROM images because that just makes the stats out of date. Now, you can actually click on this if you want to look in more detail. So you can see of the hardware stuff, networking, and then we've got various bits of USB display, VirtIO. Interrupt controllers, for some reason, we have all of our interrupt controllers in one directory, even though they're very architecture specific. If I just go back. You can look at the other bits and pieces. So for example, our target specific code, you can see the major architectures, and then as you get down to the sort of more microcontroller type things, they obviously take a lot less code. Anyway, so that's just to give you an idea of what QEMU is like. So talking about, next one. What has happened in the last year? These are the totals. 7,500 commits, over 480 pull requests, 460 developers, but it's very hard to see what's been going on with that. So this is another version of the tree map. This time, the size of the rectangles is related to the number of commits that have gone into the directory, and then this is the total number of lines of code. So you can see things like the disassembler here, very bright yellow spot, basically because we ripped out all of the C++ and replaced it with good old-fashioned C. And we can again sort of browse around and look at the, where's my cursor gone? Doing this backwards is tricky. There we go. So we can browse around and look at the individual subsystems. So we can see a lot of activity that's been going on in ARM, PowerPC, networking subsystem, VirtIO, display. They've all seen quite a lot of activity, and then falling off as we get to the smaller subsystems. I'll talk a bit more about architecture-specific stuff, but some other areas of note. Migration, block have both seen a lot of work. The TCG, I'll show a slide up later that shows quite what's happened there, but there's been quite a lot of rewriting of the back-end support. And we've also got work over the QAPI, usually quite hot because pretty much everything involves a QAPI interface somewhere, and work in the utilities. So everyone wants to know what's happening on an architecture basis. This is a diagram where I've filtered out everything that doesn't mention an architecture, so you can see what's going on. So let's look at the target, and you can see and the main architectures, as you expect, ARM, RISC-V, Hexagons had quite a lot of work, PowerPC and i386. In total, commit size, those are the main ones, but you can see architectures like LunarArch have seen a large amount of refactoring work, which is why they're relatively hot in the amount of churn. So this represents the total amount of code that has changed in relation to the total lines of code. So if you get up to 100, so almost all of the LunarArch code was replaced. We can pop back out of the target and look at the hardware support. And you can see, again, the usual suspects in terms of what architectures have seen most change. Probably the most active is, in terms of things being updated, is the RISC-V stuff, mainly because they've been adding support for ACPI and refactoring all their boot code. And then the usual bits and pieces. Most of the x86 stuff is KVM related. Finally, I just wanted to sort of point out TCG. So this is the TCG backends for all the various architectures, and you can see fairly evenly changed, and that's mainly because there's just been a lot of refactoring work to support new features in the TCG code generator. So that includes things like the physical PC relative addressing that reduces retranslations, and support for things like constants, and removing the requirement to keep track of all your TCG temps. So that's why it's a fairly even story there. Okay. And finally, this is just probably the least useful diagram that I've done for this talk, but this is just the hottest subsystems to give you another idea. Most of the work's in hardware and target-specific code, and then it falls down as you get closer to the bottom. Quite a lot of churn, but fairly small subsystems in total. Right, time for some hot takes. I will preface this to say these opinions are my own, so don't blame anyone else for them. First one, Qemu is a bit of a heavyweight. I don't know who's familiar with this graph, but this is our CI usage graph at GitLab. The reason it doesn't go above 50,000 minutes is because that's the limit of CI time we get from GitLab's open source program. So I think in 4 of the last 5 months, we have reached our CI limit and had to rely on the generous donation of extra servers from Eldon Dev to make sure that we're not completely reliant on GitLab's shared runners. But yes, our CI is a bit chunky. We also make quite a lot of demands on infrastructure. For what we think of as a small project, we're pulling 9 terabytes a month on Qemu's own servers. So this is things like people pulling tarballs, images and bunches of firmware. And until recently, we were spending $15,000 a month of Azure CDN credits to distribute that. So this is probably a good point to segue to some of the sponsors. I just want to give a shout out to GNOME and CDN77, who have just taken over the responsibility of distributing all of those heavyweight tarballs, and that's allowed us to redeploy some of the Azure credits to help with our GitLab CI usage. So that's with the Kubernetes work that's been done, we can rely more on our own resources for making sure CI runs. I better mention GitLab as well. Although we don't have a formal relationship with them, we are signed up to their open source program, and I think we're probably one of the heaviest users of their infrastructure, because we regularly burn out quite a lot of CI time. And then we have some hardware donated by various companies. We've got a ARM server from the Works on ARM program and an S390 custom runner as well. I think that's all the custom runners we have at the moment. I think there's a Red Hat CentOS one as well. So the point of this, Qemu needs you developers to think about these resources. When you put in new tests, it's great that we've got such a healthy testing ecosystem and we can test everything down from unit tests all the way up to full system tests. But these do come at a cost. And there's not really much point in having every single architecture boot a full distro 10 times, because it's mostly testing the same code. So when you add new features and you want to add new tests to test those features, please think about the resources you're using and think about how you can make your test focused and specifically testing the code that you want to test without, just adding a whole bunch of additional CPU cycles. Another thing I'd like to talk about is whether or not Quemu's diet is working. So if you look at this graph, the blue line, this is from only over the meson period because that was the easiest to gather the data. You can see we've got a slow and steady growth in the number of objects that we build in the default configure of Quemu. And just at the end, you can see it's starting to come down. So there is hope that we can reduce the total build time of Quemu, but it's something that we need to work on. And part of that has been driven by the single binary work. So a number of people are involved in this, and the main aim of the single binary work is to see if we can build a single binary of Quemu that supports all of the architectures. And to get to that point, we're starting to look at the various subsystems and seeing, do they actually need to be built for every single individual target, or can you build the object file once? So we've already done work. GDB stub is only built once, well, twice, once for Linux user, once for system emulation. TCG has just recently been refactored to build once. That saves us rebuilding a bunch of the TCG files every time. VirtIO is done, and there's going to be more to come. But I think the takeaway from this is when you add new objects into the Quemu build system, try and think, does it really need to be built per target, or does it need to be built once and shared across the whole code base? Right, finally, a little bit about our contributors. I'm not going to bore you with all the stats. I did send out the developer survey as usual, and pretty much as we expect. The average contributor is usually paid by their company to work either on Quemu part-time or full-time. We're generally a fairly experienced bunch, and we're still mostly working from home. You can see that in this little graph. So this is the dates, the timestamps of commits organized by hour in the day and day of the week. And you can see this big nice block between working hours, which is when most of the commits made. So it's not adjusted for time zone, so it's everyone's local time zone. So, and you see most Quemu developers are most effective at 2 o'clock on a Thursday afternoon. That's when. But despite the fact that we're mainly paid for it, I do want to give a shout out to the hobbyist contributors. Hobbyists and individual contributors probably contribute about 10% of the overall changes into Quemu. And if you look at their impact as a group compared to most companies who often have a lot more engineers but a long tail of drive-by commits, they have a greater impact per engineer in terms of the changes they make to the code base. So I think it's important we don't forget about how important the hobbyists are for the growth of Quemu. So this is my final graph. I think this is a plot of commits over the last year. So the size of the circle, so each dot is an individual contributor. The size of the circle is the number of commits they've made in the last year. And then along the bottom axis is their experience based on from when they first committed to the code base. And the other axis is their total number of commits to the code base. So unsurprisingly, most of the work that has been contributed to Quemu has been done by these very old greybeards who've got plenty of experience with Quemu. But we do have a few contributors that are relatively new to the project that are starting to make significant contributions. But I think we need to be mindful, if we want to keep Quemu going as a project, that we keep bringing engineers forward and keep getting them into the project and able to contribute effectively. So my final shout out is going to be to the internship programs. We've got 8 interns this year, 2 via Outreach and 6 via Google of Summer of Code. And these are excellent ways of getting students involved in the code base. We're always looking out for new mentors, so if you're an experienced Quemu developer and you have an idea for a project and you can set aside some time, please talk to Stefan and volunteer for our internship program, because it's one of the important ways that we bring people into the project. Finally, quick quiz. Does anyone know what this graph represents? No? No guesses? The amount of money should be a clue. It's an API graph, so this is how much I spent on ChatGPT to do this talk. I'm not a data engineer. I mostly code in C, so I'm working with a lot of unfamiliar plotting libraries. I was making quite heavy use of ChatGPT to do a lot of the data cleaning and do the initial versions of the graph plotting. So there you go. I told you I'd mention AI eventually. All right, thank you very much.
Hello? Shall I go? Okay. So, I'm Fabiano Fidencio. I employed by Intel, usually to fix more things than I actually can break. Usually I fail on that. I'm part of the Kata Containers Architecture Committee, and I'm here to talk a little bit about the project. I'm gonna pack 1.5 years of content in 15 minutes, so I'm gonna speak quite fast. And there are a bunch of links on my slides. I'm gonna update my slides somewhere, so take a look at that and catch me up either on the corridor or in the social events. This is what I would like to cover today. So just like a brief overview of the project, how we have been doing, milestones achieved, what we have been working on this year, plans for the future, ways to get involved, and the takeaways of this talk. Is everyone here familiar with containers? Cool, I thought I was in the wrong audience. That's the reason I put this slide here. So containers in general, everyone's familiar. Kata containers, you put that inside a very lightweight virtual machine, and that's Kata containers in a nutshell, and that makes it appropriate for this conference. So a lot of us, so previous talks were showing a lot of numbers, I sincerely think this is boring for Kata containers, but yeah. The only thing I'd like to show you guys is we have been growing on all metrics that I can get here. Apart from the number of organizations participating, this is numbers from 2022. But well, the key takeaway from this slide at least is we are a project that has a bunch of companies involved, a bunch of contributors that are not affiliated to any kind of company, but also a bunch of companies. So I consider that a very healthy metric for the project. Well, well, well. Who is David? Come on. David? Someone? Okay, I hope you guys can sit here. Yeah. No. Yep. So anyways, thanks David. I will just keep going. Yay! Really short on time, so now whoa, okay. So last year we had like our 3.0.0 release, and as the most part of the project, we just got into this let's RESTify everything. So we got our Sheen and VMM process like RESTified. This is the new runtime RS. This is not enabled by default yet, but the good thing here, the nice thing here is that, well, when you think about Kata containers, usually we had a Go Sheen that would be talking to containerd, to Cryo, that would be responsible for launching a VMM and taking care of the lifespan of the VMM. We were able to just put the Sheen and the VMM into the same process, reducing attack surface, increasing a little bit the performance. And of course, we are still going to keep support to Cloud Hypervisor, Firecracker, QEMU, and any kind of flavor of VMM that you really want to use. I would like to say that we had like a bunch of internship programs last year. Click on the link, you will see the name of the mentors, the students, and thanks a lot to everyone who actually worked on that. Last year, well, we had a bunch of talks about confidential containers. We are going to have some talks here in this conference. And I'm not going to go through this, but this is a spin-off of Kata containers. And the first official release was released like in September 2022, and this project deeply relies on Kata containers. Here are a bunch of features. Some of those have some talks linked to, some of those have some commits, things like that. Take a look at that. One of the main things that I would like to mention here is the RunK. Now we have Rust runtime, OCI, Rust runtime that can be used with Docker, for instance, and this is based on the Kata containers agent. Another thing that was really good for us as part of the community, we saw Red Hat launching a product based on Kata containers. That's amazing because we actually could validate the effort that we are doing as part of the community. And two other things is like we have a new community manager. So Triva, she was supposed to be here. She couldn't. She's on the OEF Summit in Canada. And I would like to say thanks to Sunny, who was the community manager before her, and then the architecture committee board. We are an open project and with an open governance, and we have a new member called Gary from Alibaba, amazing engineer, amazing person to work with, and he just took over the seat of Archana. And Archana, thanks a lot for the time served. More numbers, now comparing with the ones from last year. You can see we are kinda on the same pace, so we are not gonna, we are gonna match or even like grow compared to last year. Same thing here. Still a project that is not owned by only one company, that is not like driven only by the interests of one company. And let me tell you what we have been doing so far in this year. I told you about the Rust runtime. This is gonna get enabled quite soon. Like this is running all the tests that we have. This is passing all the tests that we have. And we have been adding support to other VMMs. So James Hunt from Intel added support for Cloud Hypervisor. Nubificus, which is a company from UK, added support to Firecracker. And I know that Pavel Morris, who is somewhere here, has been working on the support for QEMU. So we hope to have this enabled as part of our next major release. Last year we had support to Intel TDX. This year we had supported to AMD 7 SNP. NVIDIA has been doing a lot of work to have GPUs properly working with kata containers. And now we even have like artifacts being released with support to NVIDIA drivers, which is very cool. Another thing that is really great, at least in my opinion, is for the first time we have a true multi-arch release. We support x86, we support ARM, we support S39X, we are releasing binaries for those, we are releasing a payload that people can just get and run on their Kubernetes clusters with this architecture. On the confidential container side, this is a mess right now. A nice mess, but still a mess. We are working on a branch of kata containers. No one really likes to work on a branch. This branch has been diverged from main. And now we are just getting a lot of work to get everything back into the main and have confidential containers actually consuming kata containers, not a branch of the project. We had a lot of work modernizing the CI in order to support these, in order to have machines being plugged in from different vendors. I'm deeply involved on this. I hate Jenkins, sorry. So that's my main motivation. And right now, I'm not sure how I feel about this. Ask me in 3 months from now because it has been painful. Another thing, more internship programs we had pretty much so far till right now. The double of internship programs, as far as I remember, we had 8 internship programs between university programs plus Summer of Code-like programs based in China. And this has been amazing. We have been getting students that are coming here, staying, contributing, becoming mentors. That's freaking amazing. Another thing that happened this year that is very cool to validate what we are doing is that Azure released an offering using kata containers. So it actually validates that what we are doing is a cool thing, that CSPs are actually interested in using this, and they are actually using. So freaking cool. And architecture community changes, again. Last year we had like 5 seats, we increased it to 2, now we have 7. Feng Wang from Confluent and Steve Horstman from IBM joined us. Amazing engineers, amazing people to work with. But let me just go through quite fast about what we have been doing now. We have been working on WASM support, and WASM is trying to become a first-class citizen on Kubernetes. WebAssembly is quite amazing. And if you're thinking like, why shall I run like a sandbox inside a sandbox, we are not proposing to do that. This is going to be run on the same level as the Shin. We are trying to take advantage of Container Sandbox API. This could be a talk on its own, 1.5 hours, easily. Take it that we're going to make things simpler and improve our footprint there. Remote hypervisor, folks from Red Hat are familiar about this, called like peer pods, Cloud API adapter. This is a way to run kata containers without needing to do nesting virtualization, which some providers do not actually provide you the ability to do so. So you just like start a VM on your CSP on the same level as your KVM. So that's very cool for the project. We are doing more GPU improvements, not only from NVIDIA, but also from Intel. And we are trying to do like community meetings that are a little bit more more friendly, on a friendlier time for folks based in Asia. A bunch of our community members, a bunch of our consumers are coming from China. So we want them to feel as part of the community as they should be. Next year, we are going to do our major release. Hopefully, we're going to have everything here included, including your contributions. Do you want to know how to contribute? Well, go there, katacontainers.io/community, reach us on Slack, and remember, YO ideas are always welcome, and we do welcome those. Hands-on contributions are even better. We lack help. We need help. And the takeaways that I would like you guys to leave this talk with are, we are a health community. We have been growing. We have been following open governance, so anyone can become part of the architecture committee. This is election. Just go there, do some work, become known in the community and you have your space there. There is a lot of work to be done, really. There is a lot of areas to be improved, and we really would like to have you as part of the contributors of the project. And that's it. Thanks a lot. I'm here on behalf of the Architecture Committee of Kata Containers. Thanks a lot for your time, for your patience. Thanks, David. And that's it.
Hi, everyone. I'm Michael Roth. I'm from AMD, and I'm here to talk about accounting and page migration challenges in secure guests using FD-based private memory. So currently, user space uses the malloc, mmap, and related interfaces to allocate memory, and then it uses those virtual addresses to tell KVM what pages to use to back guest memory through the nested page table. And over the course of developing hypervisor support for confidential guests that support AMD's SEV SMP technology and Intel's TDX technology, a need has arose for a different way to handle how we allocate and assign memory to guests. And essentially it boils down to using a file descriptor and an offset instead of the virtual addresses that are allocated to user space. And certain challenges arise in moving to that model, and that's sort of the focus of this presentation. So just to give you some more background on FD-based memory, the latest implementation of that is called guest memfd, or GMEM for short. You might also hear it referred to as unmapped private memory, or UPM, and it's essentially a way to back private guest memory with pages that can't be mapped or written to by user space. And there's some benefits to that, like it'll help protect against tampering of guest memory for user space, but since SEV, SMP, and TDX both have hardware protections against that, that's not really the main driver of this. The main driver, or one of the big ones, is the fact that with TDX, if user space touches guest memory, that could cause a machine check. So there needs to be a way to prevent that from happening, and it's sort of tricky to prevent that if that guest memory is mapped into user space. Another benefit of this is that it provides a way to partition normal guest pages, the shared pages, from the pool of memory that's used for private guest pages, and that ends up being really useful both for TDX and SEV SMP to avoid dealing with how we deal with issues like if the host is trying to access shared memory and the guest flips the state of that page to private while the host is trying to access it. We need ways to deal with that probably involve adding hooks and locks all over the place, but by having two separate pools of memory, when the host is accessing shared memory, that memory is always going to be shared, and when the guest switches to private memory, it's just going to start mapping memory from a different pool instead of changing the state of the memory that a host might be accessing. So let's look at how that's plumbed into KVM in a bit more detail here. This is how things work currently without GMEM, with normal guests, and also with SEV and SEV ES guests. So if you look on the right side here, we have a guest page table. It's got a GPA mapped into its page table for address 2000H, which is just normal shared memory, and then it's also got a private page at 3000H. And in both of those cases, if the guest tries to access that GPA, if it's not mapped into the guest's nested page table, then you'll get a nested page fault, and then the KVM MMU will then look at the mem slot and figure out what host virtual address is supposed to back that guest physical address. And then from that host virtual address, the KVM can then find the host physical address that corresponds to the page that should be mapped into the nested page table. Now with GMEM, there's now a notion of a private mem slot where for normal pages, things are still handled the same way, but for a private page, KVM now has this X array which tells the KVM MMU whether or not that page should be backed by private memory. And in cases where it should be backed by private memory, when we look up the host physical address of the page that we should map into the nested page table, instead of relying on the virtual addresses, we rely on the offset corresponding to that GMEM FD that user space passed to KVM. And as far as how we assign whether or not a guest should be, a guest page should be treated as private or shared. That could happen in a multitude of ways, but the main one is the guest can do what's called an explicit page state change, where it issues a request to the hypervisor to switch the state of the page from shared to private or private to shared. And with this GMEM model, what will happen in that case is that the hypervisor will get the request and forward it to user space in the form of a KVM exit, VMG exit, and then user space will then tell KVM that that GPA should now be treated as private using a new KVM set memory attributes ioctl. And there's another similar case for implicit conversions that basically happens the same way, so we don't need to go into much detail there, but this is sort of how things are implemented with the current hypervisor patches for SEV SMP support that have been posted upstream. Those are currently at version 9 right now. And things work pretty well with this model, but my colleague, Nikunj Dadanya, who couldn't be here due to some visa issues, he's been looking at some follow-on features for SEV SMP hypervisor support, like page migration, which could be useful for a number of things. One of the more common ones is memory compaction. If you have a bunch of pages that are being used for private guest memory, because that's the main workload that the host is using, by not having support for page migration, you could potentially run into issues with fragmentation, and depending on how the guest access patterns are, and also things like NUMA rebalancing rely on page migration. So let's look at how we'd implement page migration with GMEM in the mix, and let's look at that in the context of memory compaction, which actually ends up being one of the easier scenarios to deal with, but still has some issues. So with memory compaction, there's a kcompact D kernel thread that periodically runs, and essentially it takes allocations that are scattered around the host physical address space and tries to migrate them to denser regions of memory so that we free up more of the host physical address space for larger allocations for things like DMA buffers and transparent huge pages. And one of the main interfaces, or the common interfaces that memory migration users will use, is the migrate pages interface. And just a few parameters there, but the more important ones are the from list, which is a list of pages that that we want to migrate, and a new page function, which is what allocates the target pages that we want to migrate to. And the migration in this case, or in most cases, will happen in two phases. There's a migrate folio unmap sequence, which will look at that page, and then it will look at the reverse map, which contains a list of all the VMAs across all the processes in the system, and determine which processes might have that page mapped into their virtual address space. And for each of those, it'll unmap that page from that process's page table, and then it will also issue MMU notifier events to let those processes know that that page is being migrated and that the process shouldn't attempt to, use it or map it until that notification sequence is completed. But one issue we run into here is that with GMEM, we never map that page into user space. So when we're trying to determine whether what processes we should send those MMU notifier events to, we don't see any VMAs, so we don't send any notifier events to any processes. And that becomes an issue because the KVM MMU is one of the subscribers to MMU notifier events. And normally in response to something like this, it would unmap that page from the guest's nested page table so the guest wouldn't be trying to access it while that migration's happening. And that doesn't happen here, so that causes problems. And the next stage of migrating the page is when you do the actual copy of the source page to the target page, there's a migrate folio callback that's sort of registered by the gmem instance, and that callback is what will actually handle copying the source page to the new destination page. And there's some generic migrate folio callbacks that various FD-based memory backends might be able to use, but in the case of confidential guests, we run into issues because generally you need hardware or firmware support to actually do that copy, or else the guest will treat that as its memory being tampered with. And that's not really an issue with gmem specifically, but it's just something that gmem needs to be able to handle if we're to support page migration. So one possible solution here is that the migrate folio callback, since it's aware of all these things, it can implement the hardware and firmware support that's needed to do the actual copy. And in terms of the MMU notifier events, because gmem is actually specific to KVM, it's not going to be used anywhere outside of KVM, it's not such a bad thing to have that migrate folio callback also sort of manually issue those KVM MMU invalidations to make sure that those pages get unmapped from the guest's nested page table. And so with those things in place, things sort of work out for a compaction, but as we start looking at other use cases, we start running into other issues that sort of result from the fact that this memory doesn't have any associated VMAs with it. So let's start taking a look at that. So in general, memory that's allocated by gmem is basically accounted by the host as page cache allocations. It's not accounted to any specific process, and that's going to end up causing problems if you're trying to set process limits on how much memory a particular process can use, or C group limits and things like that. Because it's just sort of treated as page cache, those things aren't really taken into account the way you'd expect normally. So one example here is we have an SMP guest that has 40 gigabytes of memory that through NUMA-CTL has been instructed to allocate evenly between NUMA nodes 2 and 3. And in this case, SMP guest isn't using lazy acceptance or anything like that, so at boot time it's actually going to touch all 40 gigs of that memory. But if you look at the resident set size of the QMU process that's running the guest, it's only 85 megabytes. So if you're trying to place any limits on memory usage, the normal mechanisms aren't really going to work out here. And also, if you look at things like NumaStat, you're not going to see that those pages were actually allocated from node 2 and 3 based on the NUMA policy, but they're not going to get accounted to the QMU process, even though if you look at the overall file pages usage, you do see that they are coming from nodes 2 and 3. And if you dig a little bit deeper into why that might be and start looking at things like proc files, if you look at NUMA maps, there's 4 files listed here, and they have useful information about like how many pages are allocated to a particular node. But in the current implementation of gmem, for every one of those fd-shared files, there's a corresponding fd-private file that's not showing up here. And the main reason that it's not showing up is because the way these things are listed out is basically by walking that reverse map, looking at all the VMAs of that process, and then sort of listing them out here. But because there's no VMA, we don't see that. So it seems like a lot of these issues sort of stem from not having a VMA associated with the memory that's being allocated through the gmem file descriptor. So maybe one of the simplest solutions is just to kind of give the kernel what it wants and allocate some sort of shadow VMA or invisible VMA, so that all of this accounting stuff just sort of magically starts working because there's now a VMA that's tracking that. But it ends up not really being that easy. You obviously needs to take care that those mappings don't actually result in that memory being mapped into the process's page table, or else you'll run into the issues that GMEM specifically is trying to avoid. And also, just having VMAs isn't enough, because a lot of that accounting is going to happen through at the time that the page is actually faulted in and touched, not just when that VMA is created. And because there's no normal page fault mechanism where that accounting would normally happen, we sort of need to kind of duplicate that accounting somewhere in KVM when we're actually pulling pages out of that GMEM backend to back the guest memory. And there may be other solutions that could be pursued, but nothing that's clearly or necessarily better. And since I actually thought I wouldn't have time to cover it, there's another issue here, which is with NUMA bindings. I had mentioned, I had the example earlier where we used NUMA CTL to set what nodes the guest memory should come from, and that actually worked out pretty well, but that doesn't help too much in the case of QEMU, because QEMU tends to use mbind to handle setting NUMA policies, so that it could do things like have two virtual NUMA nodes and map those to the actual physical, or pin those to the actual physical NUMA nodes on the host to sort of mimic the host NUMA topology. And NUMA CTL doesn't really help with that sort of thing. So underneath the covers, a lot of the QEMU interfaces to handle NUMA bindings rely on mbind. But the issue with mbind is that it takes a virtual address, and because we don't have a virtual address for that private memory, we can't use mbind. So I think there's been some discussions upstream about potentially introducing a new fbind ioctl that can do what mbind does, but do it given a file descriptor and an offset. There's other potential ways that we could potentially approach it. One of them is that, because there's generally going to be a shared memory allocation for a particular range of memory that sort of corresponds to that physical allocation, that private allocation of memory, and it's really just that X array that's telling the KVM MMU where to grab each particular page from the shared pool versus the private pool. So maybe it makes sense to sort of just mirror the NUMA policies that are set on that shared pool to the private pool, but in some cases maybe KVM's not aware of how those policies are being set on that shared pool and doesn't necessarily have the insight or get called at the appropriate times to make something like that happen. So that's another area that is worth looking into. But in summary, GMEM provides some very critical infrastructure that's needed to finally enable confidential computing in KVM for things like SEV, SMP, and Intel TDX. But when we start looking at things like page migration and memory accounting, there's some gaps that remain there. And the current implementation for users that really put security above and beyond all these other things is probably sufficient, but we will probably need to address some of these other gaps, and some of the solutions could potentially be fairly involved and complex, so we could definitely use some help from the community and any of the memory experts to make sure that we can find the right solutions to some of these issues. And I think that's it. If there's any questions. Sure. Yeah, I mean, I would certainly prefer sort of a staged approach if possible. There are areas in the kernel where will allocate things like pseudo VMAs to help with the accounting. So it's not like this is, you know, the first time anybody's looked at taking that sort of approach. So it, you know, it's possible that we could just sort of work it in the next version. And maybe for some of the memory accounting stuff, you don't even really need to address the VMA thing. Maybe it's okay that some stuff like numastat and some files don't show up in proc, but maybe as long as we at least do stuff like account the memory that's being used by GMEM to the guest's resident set size, maybe some of the more important policies will at least be honored. So there might be, you know, smaller, I guess, you know, fixes that could be made to enable, you know, some of that other stuff. Sure. Anyone else?
I was wondering whether it would be possible to, instead of unmapping this memory, just making it inaccessible by, for example, setting a reserved bit in the page table instead of completely unmapping the memory. But we'd allow to keep the DMAs around and would allow other code to do the migration decisions. They can usually be on the reserved bit set.
Mm-hmm.
So could that be a possible solution? What do you think?
Yeah, I mean that's sort of what I was thinking of with creating those pseudo VMAs. If you took it to the extent that you actually mapped it into the process page table, so that basically everything works the same way it does with normal memory, that would solve a lot of solutions. But then you need to make sure that there's a way to map it into the process's page table in a way where if that user space process try to access that memory, all the same protections still remain in place, where you can't write to that memory, and there could be potential complications if there's restrictions on whether a THP mapping can overlap with a private mapping, where even if you don't actually write to a particular page, maybe the fact that you're writing to a huge page that overlaps with a page of that sort, you know, there could be some issues that need to be looked at in finer detail there.
PHP probably needs interaction with the guest because the guest needs to know which pages are split up and it has to use 4K and trigger mappings, right? So, but I think everything else will probably work with when the DMA is around and just it's just inaccessible because of reserved distance, right?
Yeah.
Everything is still in enough places that could be a bit more memory.
Yeah, that would be my hope, because it seems like it would solve a lot of problems if it could be done that way. Yeah. Question in the back? Hi. Hmm. Okay. Yeah, I wasn't aware of any previous discussions around that, but maybe it makes sense to revisit some of those things in the context of GMEM. Well, if there's no more questions, then I guess that's it. Thank you, everyone.
Computing. So let me quickly review what we are going to talk about today. First, a quick overview of what confidential computing is about. What is attestation? The use cases for confidential computing, bonus points for whoever can identify this picture. Going from root of trust to actual trust. A number of platform-specific details. And the supporting technologies. This picture is more difficult to identify. It's the foundations of the Eiffel Tower. So this is really a summary. I'm going to speak relatively quickly and brush quickly over various topics because the details are in a blog which you can find following this link. So it's a 6-part series blog on Red Hat blogs. So first, what is confidential computing? It's mostly about protecting data in use. This is a quote from some guy you maybe heard about. I compromise the confidentiality of their proprietary software
to advance my agenda of becoming the best at breaking through the lock, from Kevin Mitnick. So, you know, hacking has always been a way of trying to go through the locks. And so the problem statement here is really that we have infrastructure that is designed to protect against the workloads inside and not the other way around. So the software you have today mostly runs on hardware you do not run, like for instance a cloud provider, a virtual machine host of some kind or whatever. And in there you have various resources. You have CPUs, memory, disks, networking, and so on. And for instance, let's say you run containers inside. All the mechanisms of sandboxing inside are designed to protect against the containers accessing these resources. They are not designed against the infrastructure looking at the containers. And that means that if you want to run, for instance, Apple and Samsung or competitors on the same hardware, you'll have a problem because there is no guarantee that someone is not going to spy on both or transmit data from one to the other. So we have good solutions for disk and networking. You can do disk, I/O encryption and so on. And for memory, essentially the memory that you have is in the clear to any one of the hosts. You can dump the process of QEMU or whatever and see what's inside. Actually, I'm going to give a talk at DEF CONF precisely about that. Now, with memory encryption, you have some kind of weak encryption, and so it's intentional that the encryption being used here is relatively weak, but at least it's something that protects against immediate tampering and accessing the data. Other levels of protection include being able to protect against, interrupt tampering or injection of faults, corrupting the CPU state, etc. This is, for instance, the difference between SEV, ES, and SEV. We're going to see that in a moment. So another important aspect, and that will be most of the focus of this talk, is attestation, which is essentially to prove that what you are running is what you want to run and that you are running where you want to run in a setup that you can trust. Okay, the origins of the root of trust, you probably heard about the TPM, and that was hardware root of trust. And it measures and launches the next stage, and the next stage records its own state, and then it keeps going that way and again until you reach, for instance, the Linux kernel or the workload. And at some point you have a record, a faithful record stored in hardware of everything you did. So this is essentially how you build the root of trust, for instance, for secure boot or things like that. The chain of trust. Now, if we want to do something like that for more advanced workloads, and here I'm taking the example of Kata containers that Fabiano just presented, then we want to have some additional levels of trust that we can provide to the higher levels. So first, we need to provide a kind of trusted platform that will offer some kind of confidentiality guarantees that are enforced by hardware and cryptography. And that way, the platform simply gives you the tools, but it does not really, you don't need to trust the platform except for the fact that it does the computations the right way. And then you have the host that will manage the physical resources, give you, things like CPU, memory slices, and so on. But in the new approach, you will not have to trust that your data in there is visible. And finally, in green, you have all the aspects that belong to the tenant or the owner of the workload. And that's a confidential area, and you want to make it completely inaccessible to the host, even while it's running on it. Okay, so what are the kind of guarantees that confidential computing really provides? Well, it's really about confidentiality. That's the thing that matters. So it protects data in use from leaks or from tampering. It's not designed, for instance, to protect against any kind of crash. It's not designed to protect the disk or the network data. You need to do that yourself and keep doing it, or even better, in a confidential computing setting. And of course, it does not offer any guarantee of quality of service, not even forward progress. So it's possible that you can do, it's preferable in this context to say the guest will no longer make any forward progress or the guest will crash than to leak data. That's essentially what it means. That message is difficult for people, for instance, in the kernel community. They really have, many of them have a hard time saying, I'm okay with the idea that we no longer trust PCI, for instance. And it's hardware-based real-time cryptography, which means that with sufficient resources, you can probably break it, but not in real time. That's essentially what you're... Now, all these productions are highly implementation dependent, even within the same vendor. The chart you have on the right here is for AMD devices, depending on the generation, SCV, SCV-ES, SCV-SNP. So the bottom line of all this is there is, when you say confidential computing, it doesn't bring automatic security any more than the guardrail protects you against accidents. How fast was this car driving? So what is attestation? Essentially, in our case, it's proving that you run what you want to run and where you want to run it. That's essentially the two questions we try to prove. Now, let's start with a bit of terminology, and I'm going to present the RATS model from the ETF, so that's remote attestation procedures. And so we start with a verifier component that essentially is going to implement the logic of checking. You endorse a particular piece of hardware, and so you provide some kind of endorsement. You also, as an owner, need to have a number of reference values that you're going to be able to provide to this verifier, for instance, the identity of a VM or stuff like that. And you also, as an owner, will be responsible for the appraisal policies of the evidence that is being presented. Now, when an attester tries to present that evidence, it presents it to the verifier. You run through the things that the owner provided, and you end up giving attestation results to a relying party that is whatever is going to, for instance, deliver keys or secrets or whatever. And the relying party owner also has its role in appraising the evidence or the attestation results. One example of this, and I'm going to talk about this later, is that you can decide to no longer accept a workload that you used to accept because you've discovered some kind of vulnerability in it. So the basic concept of attestation is really that you're offering some kind of proofs about the configuration of a system. So in general, generally speaking, not just for confidential computing, attestation proves some kind of property of a system. That's what it means. And when we talk about remote attestation, that means that we decouple the evidence from verification. And the lock and the key is a good example where the key itself is remote from the lock. And say you gave a key to someone and you no longer want them access to your property, you can change the lock and now they can no longer use that key to enter that property. Now there are two big models for this evidence check. One is called the passport check model, where you present the evidence given to you by the verifier to the relying party. So it's like you're presenting a passport, and that's, for instance, what Microsoft Azure does for most of their secrets. And you have the background check mode, where you instead validate the evidence in the relying party itself. So I'm also going to use, and I use it more in the blog than in this talk, but I propose what I call the remits pipeline. It's a simplistic model of trust chains that can be used to compare various trust chains with one another. So R stands for root of trust. It's mostly things like certificates, etc. E for endorsement. That's, for instance, a signing key that might be in a CPU or something like that. M for measurements. That's typically, in our case, you summarize a measurement with hashes and you certify the hashes. I is for identity. So for instance, reference values that you're going to compare with the reference values you have in your provider. T for trust, and that covers things like policies, deciding whether you trust this or that specific hash. And S for secrets, that's usually how you unlock the system. You give back a decryption key or something like that. And I find that remits, you remit the secrets. It's sort of easy to remember. So some examples of this for secure boot, for instance, you start with a TPM. The endorsement is made by the manufacturer that says, I actually signed that chip, or I endorse the chip. The firmware bootloader is where most of the measurements are going to be, the measurements that matter are measurements of the firmware and the bootloader. And then you're going to expose that through a signed attestation. That's essentially the evidence you can carry around, or a hash or something like that. And then you have attestation policies, for instance, in your provider that will decide, do I trust this particular boot or not? And finally, you release that through, for instance, a cloud API secret. And that's what you get back that will allow the workload to proceed. It can be the root disk, it can be your workload, it can be anything. Now, when you sell a property, you have the same kind of chain. So that chain is relatively general. So for instance, you start with a notary as a root of trust. You have signed records as the endorsements. You have deeds or affidavits as a measurement. A description of the property is essentially the identity that you find on these deeds. And the fact that you exchange money is the way you decide to trust or not what you got, and then you give money for it. And the secret you get is you get the key of the new property. So that's the same principle. And our whole money system is really based on that, where we used to have gold or silver as essentially the root equivalent of what you have. The government was the endorser of that paper note that you get. The market value is giving you an evaluation of how much $20 mean. And the number of dollars is really the identity of the transaction. Handing over cash is what you do with that, and getting foods or goods or whatever is the secret that gets released. So that you see that pipeline can apply outside of computer science. So when we apply that to our confidential computing case, I'm using Kata containers or confidential containers as an example here. We measure what we run using various cryptographic tools. And so we can have, for instance, pre-attestation. That's the case of SCV or generation. You measure the payload before allowing it to start. Or you can have post-attestation, where the code in the payload can confirm its identity, and that includes, in that case, it can include something that is much larger. And that's what is going to unlock the secrets ultimately. You can actually extend that to the whole workload, so you can decide I only unlock secrets if I know which workload I'm running. Okay, so there are various use cases for confidential computing. It's a continuum from virtual machine to whole clusters. So the base is confidential virtual machines, and it's funny that this picture is what you get on DuckDuckGo when you search confidential virtual machine. I don't know why. Then you can have functions, and a good example of that is confidential workloads, a product called KVM. You can have something that is more orchestrated, and that's the case for confidential containers that Fabiano mentioned earlier. And you can have the whole enchilada, you can have the whole cluster. So for instance, today we have something called Constellation that will deploy complete virtual machines. So the confidential virtual machine is really the basic technology behind it all. It starts with new firmware and hardware APIs exposing new features, and they are mostly platform dependent today. The host kernel is no longer trusted, but it still has to expose new features to expose the new features. So for instance, through new devices. DevSCV is a good example of that. The hypervisor is no longer trusted. And again, that's something that is really a hard pill to swallow for prominent members. Greg Cage, I'm not mentioning your name here, of the community, who say, that model is completely broken, PCI has to be trusted. No, if the hypervisor is lying to you, it can put anything in the PCI space and essentially try to crash the guest that way. Now the VM becomes a confidential enclave. Inside you have guest firmware, the boot sequence is measured. You can ask Gerd how to do that, for instance, or Dan, or the guest kernel also can be measured. And so that's essentially the basic technology. Now the next step is trying to have a lightweight and quick container-like experience. And the example you see there is KVM VM. So in that case, what you see is not really running a confidential workload. I'm really running it on this laptop to show that I can essentially have an Ubuntu environment from a Mac laptop. And that's real time. The speed you see is real time. So it's really very fast in terms of user experience. So the VM is presented as a library to the OS through a project called libkeren. There is a direct integration with Podman, so you have a container-like experience. You don't have orchestration, it's really Podman, so it's the command line. It got very early support for SCV, including, that was, to my knowledge, the first working remote attestation that was implemented in this project. Now, back to Kata containers, that's the next step. That's designed more for orchestration. Fabiano mentioned the Sandbox API. That's essentially the new API to interact with things like Kubernetes, etc. And that gives us a way to schedule a large number of containers, orchestrate them, and so on. And so in that case, you have the same set of components that need to be changed the same way as before. It's really the same technology, except this time we run it to treat a VM as a pod so that we have this runtime that runs container through VMs. So the big difference for the confidential containers project is that now it needs to rely on this relying party on the side and perform this kind of remote attestation to decide, do I run this workload or not? So same steps I'd already described, but please remember these are really the important steps. And if you go one level up, you can have the whole cluster deployed that way. So what you see on the right is constellation, edgeless constellation, which is essentially creating. So this one is not real time. It takes quite a few minutes to actually boot things. But what it does is set up for you a set of SCV-SNP enabled VMs, and in minutes you have a cluster with the whole integrated, checked, and so on for you. So that's really convenient. In that case, you make the whole cluster confidential. It works at the cloud provider level. So the example that I gave here, I think, is Azure, if I recall correctly. And it generates, as I said, fully confidential nodes with encryption and everything. They have some interesting aspects to it, like an attested form of TLS that lets multiple workloads attest one another and make sure that the other side is running on a trusted node as well. And for instance, they also have this joint service, which is a way to attest nodes. I'm going to talk again about this in a moment. And a verification service, which is for users to verify that the cluster they run on is trusted. So how do you actually build trust? You want to keep the trust alive along the way. That's the part that is difficult. So how does this work in practice? Typically, you have a cryptographic measurement of the enclave. So it can be varying aspects of the enclave. In the case of Kata containers, we are trying to at least be able to check the workload we are talking about. And then you're going to send some sort of ID in the passport model saying, that's me, or it can be a measurement, it can be whatever. And in return, after attestation, you get some kind of keys. But of course, as I said, the benefit of having this remote attestation is that you can decide to deny it, even for something that you allowed before. So you can change your mind if something gets broken along the way. So the attestation flow, in that case, is to unlock the workload by giving secrets. So the attester first sends a request to the relying party. The relying party first responds with a challenge. The challenge is essentially so that we have a nonce somewhere in the process to avoid replay attacks and these kind of things. And then the attester can encrypt the evidence using the nonce and essentially produce a quote that way to the relying party. Now that gets presented to the verifier. The verifier says okay or not okay. And if it's okay, you can get the secrets from some kind of secret broker. That can be a completely different service. It's the case in the case of Azure, for instance, that's a completely different step. And then you give back the secrets that your workload is going to run with. So that's relatively simple. And below is the remits model for this kind of thing. So one important aspect of attestation is that there are so many variants. One of the key factors to understand is who proves what to whom. And you have different kind of proofs for different consumers. So for instance, there is something I call system-facing attestation. That's system software wanting to build some kind of trusted execution environment. You want to make sure that, and that's the case when you boot, you do a secure boot inside a confidential VM. You have user-facing, that's the user wants to verify that the system they're using or connecting to is trusted. So you provide now, that's a verification service in the case of Constellation. You have workload-facing, which is something that is more API-driven. It's a workload wanting to prove I'm running on a confidential system and I won't run otherwise. That's what Kata containers does, for instance, or confidential containers with Kata. You have peer-facing, so workloads are trying to talk to one another and checking if the other workload is trusted, and that's ATLS in the case of Constellation. And you have cluster-facing, it's whether a node in the cluster accepts another node joining. And that's the joint service in the case of edgeless. So the thing is that, of course, as you can guess, there are many platform-specific details. That's what makes it salty and interesting. Beyond that point, there'll be zombies, as they said in the roadmaps. So different vendors have relatively different approaches. AMD Secure Encrypted Virtualization, for instance, has a separate secure processor that does a lot of the work. And SCVES added, SCVES added encrypted state. So for instance, the register file is itself encrypted. And SNP, or Secure Nested Pages, adds, among other things, protection of hostile memory mapping and integrity protection for interrupts and stuff like that. Intel has a different approach with TDX, Trusted Domain Extension, where they run things on the main processor and have a new secure arbitration mode that will be a slightly different, well, it has higher privilege if you want, and can control the trusted enclaves. And they implement modules with that, so that we essentially have to treat as binary blobs, for the moment at least. So it's a different approach in the sense that it runs all on the main CPU, not a separate CPU. And then there is IBM Secure Execution, which has 2 generations of it. You have the details in the blog if you want to have more links. PAR has a protected execution facility. HARM has confidential computing architecture. And all these technologies share one thing in common, that they are based on virtualization. And for some reason, they all work completely differently internally. So you really have to, at the moment, it's not really easy to present a single view of everything. So AMD SCV is interesting. It's really the messy kid of the of this space. It's the first generation. It was somewhat flawed. It provides memory encryption through hardware. Again, built on top of virtualization. There is a non-virtualization equivalent called secure memory encryption. It relies, as I said, on a separate security processor and only features pre-attestation. Now, the problem is that there were many vulnerabilities discovered that gave it a really bad rep, and that bad rep persists to this day in the kernel community. So when you submit things related to SCV, even SNP today, the first response from various community members is, your stuff is broken, fix it. Not looking even at the reasoning or whatever. ES and SNP were essentially the cleanup crew to this initial state. So protecting the CPU state. ES does not really change the attestation model. SNP protects against malicious page mapping and other things. But the most important thing for us is that attestation can now be done from within the guest. The guest can get the attestation quote and send it over, so that gives you much more flexibility in terms of how you do attestation. And the other interesting thing is virtual machine privilege levels that give additional protection levels from within VMs and can build interesting stuff like virtual TPMs. There are talks later today. I'm going to talk to mention them. Finally, the other big player is Intel TDX, Trust Domain Extensions. So SGX is the base technology, the non-VM virtual machine-based one, to create secure enclaves, and that's still used. It's funny because it's deprecated outside of Xeon, but it's still used for TDX to build the enclaves that they use. So TDX is virtualization-based. There is no separate security processor. As I said, new secure arbitration mode, and various binary modules to expose the required services, so you have a big trust Intel component to it. It's actually the case with AMD as well. The attestation in that case is performed by a quoting enclave, which is, again, a secure enclave running on the same architecture. Finally, let me quickly brush over various supporting technologies. So that may concern many of you. Of course, we need host and guest Linux kernel support. So for instance, we still have a lot of the important features not mainstreamed on the host side. We need hypervisor support, obviously. We need guest firmware support, host provisioning and support tools, like for instance, LCVCTL, to be able to say, I actually endorse this host. Generate key brokering service and attestation. That's an area where the Kata containers community is probably going to provide some stuff to the rest of the world, because we were sort of first in this area, And we are now trying to make sure that this can be used, for instance, for clusters. Can we use the confidential containers attestation mechanisms for clusters, these kind of things. And then there are all sorts of compatibility layers. Like for instance, there is all this work that has been done for physical TPMs. And so one of the way to present that level of confidentiality to a guest is to have a virtual TPM. And there are talks later today that talk about this. And one implementation, for instance, is secure virtual machine service module. There is a talk later today. So let me refer you to the blog for pointers. Again, I'll give you another opportunity to flash code. Upcoming attractions later today in this space, so watch out for these talks. At 2, we have Trusted I/O with January Powell. At 2:30, we have Secure VM Secure Service Module, the SVSM I just talked about, Jörg Röder. And at 3, we have Zero Trust Virtual TPM, again, what I just mentioned about TPM. So, in conclusion, attestation means many different things to many different people. The key takeaway is, first of all, that we only scratch the surface. Confidential computing is really a large collection of technologies. Attestation can mean very different things, even in the same context. Preserving the chain of trust reliably requires a lot of careful thinking. Technologies are not consistent, so we need to really have adapters all over the place. And for details on what I just showed, there is this QR code here. I'm going to show it again in a moment. So, but if you want to take it, so same QR code here. Now is a good time for questions. We have like 0 minutes. So this is related on the internet, right? They heard it. I don't have to repeat the question. They heard it on the, yeah. Yeah. So that's a very good question. So I think this is one of the reasons for the push behind things like VTPM, is that they essentially rely on an interface that has an ecosystem built around it, and so you have things like Keylime, etc., that will let you validate physical TPM just as well as virtual TPMs in a way that is somewhat independent from the operating system you're running inside. Now, Keylime is a specific form of attestation. I did not really mention that, but they are sort of non-blocking attestation. It's after the fact. You know, you run your workload, and after the fact, they tell you, oh, this was the wrong one. But they don't have a blocking mode yet. They're working on it. As far as knowing that you can trust this or that guy, it's really the usual crypto stuff, in the sense that you will rely on things like certificate chains, and so on. So all the attestation technologies that I know of today are built on relatively standard crypto standard. Now, there are many cryptographic standards for that, but typically you verify things using standard crypto libraries and so on. So they are not reinventing the wheel, if you wish. Does that answer the question or not? Yes. Yeah. So the problem is that you have two opposite trends there. So one side is the confidential container side, for instance, the open source community. And what we did is we built, the first thing we did is we published the protocol we are going to use for attestation. but being lazy bums, we essentially did not implement it. And then Sergio Lopez wanted for confidential workloads to have remote attestation. And so he said, oh, they have the protocol written up, let me use that. And he implemented the confidential container remote attestation protocol and server, etc. And I said, oh, your stuff is broken. It doesn't have a way to register workloads. And so he sort of added some API calls to it that were not part of the attestation protocol, but what you need to have key provider, how do you register keys and stuff like that, right? Which in our design was separate, but of course he needed that. So in his broker, he put everything together in one piece. And as I said, that was the first one that worked. And then we actually did work with this for a short while. And relatively recently, maybe 2-3 months ago, there was a major decision to essentially not follow up with that, but instead have a design where we have per hardware driver, both on the key broker client and key broker service side, to address all the differences between various platforms. And then we have a common layer for the transmission of information, exchange of keys, URIs, all these kind of things. So now, the way this was done is relatively generic, but within Red Hat, for instance, we are discussing how to build attestation services for clusters. We're looking at what Edgeless Constellation is doing. And in that context now, the question is, does the stuff that Confidential Container did apply? Can we actually extend it to have joint service equivalents, to have verification service equivalents, these kind of things? And surprisingly, the answer is not quite, but not too far away. So, yeah. Thank you.
All right. Good morning, everybody. My name is Suzuki, and I work for ARM, and I'll be talking about the ARM CCA architecture and the KVM support work that we have been doing. So here is the brief agenda. So primarily, I'll be spending more time explaining what the ARM confidential compute architecture is about. Oh, that's not good. All right, that's not good. Not yet. Yeah, all right, okay. And then we can talk a little bit about how we support this in the KVM and where we are right now and what the future plans are for the ARM CCA. Right. So the fundamental foundation architecture, hardware architecture for the ARM CCA is called a realm management extension. This is an ARM v9 feature. What that brings us is two new worlds. So traditionally we had secure and non-secure world on ARM based on the trust on technology, and we have, as usual, 4 exception levels like the privilege levels. EL3 being the highest and EL0 being the lowest, where you run the user space, and EL2 is where we run the hypervisor / kernel. EL3 is where the most privileged firmware resides. So the RME, what it introduces is that it adds 2 new worlds. It moved the EL3 from the secure world into its own separate world called root world, and only EL3 is available in the root world. The secure world only has EL0 to EL2, and the non-secure remains the same, and there is a new world called realm world, which again is similar to the non-secure world, EL0 to EL1 and EL2. So, what's the next slide? And additionally, the architecture adds a new check in every translation or every access is called, you can think of it as a stage 3 access. So traditionally we have had 2 stages of translation on ARM. Stage 1 translates virtual address to an intermediate physical address, as it's called. And there is an optional second stage translation which converts the intermediate physical address, which is your guest physical address, into the actual physical address. And the result goes to the system bus. But with the introduction of RME, we add another check, which is called a granular protection check. What this basically does is checks each access against this physical address state that it is supposed to be. And it is maintained in a separate table called granular protection table, and this is under the control of stage 3, the root world in EL3. So what that brings us is you can dynamically change the physical security state of a granule at runtime, and you can move pages from non-secure world to any other world, like the new world called realm. So those are the fundamentals of the architecture that ARM gives you. And on top of that, ARM has built a reference software architecture which enables you to run confidential compute VMs. So you can see the new realm world in the middle. As usual, we have the EL2 level where we run a hypervisor stub. It's called Realm Management Monitor. It's a software architected software component which provides services to the normal world to manage confidential compute VMs. And it also provides some services to the virtual machines running inside the realm world. It's called Realm Service Interface. And it can talk to the EL3 firmware to manage transition of the pages into different states. Right. So as I said, the ARM-CC architecture, what it does is it takes away the access to the virtual machine private data and stages, metadata, and it allows the non-secure host to manage the virtual machine using management interfaces. And the RMM is part of the Realm's TCB, and this is an architected software component, and the specification is at v1.0, and this is at ESC2 level now. So this is going to be finalized soon in a couple of weeks. And there is a reference implementation from the trustedfirmware.org, which is called TFRMM. This is public right now, so we are at beta 1 at the moment in terms of spec compatibility. The RMM the component is loaded by the EL3 firmware at boot. This is to make sure that you can trust what is loaded at RMM, and this is part of the platform attestation report that you get out of the RMM, so that you can verify that nothing has been tampered with and you are running what you are expecting. And the RMM specification essentially defines what are the services that you provide to the host as well as to the guest. So those are different interfaces. I'll come to the later. Yeah. So in terms of services to the non-secure world, you have the RMM version called that tells you what is the version of the RMM that I'm running, so that I can expect what are the ABIs and semantics. And then it also provides you a way to know what are the features that an RMM supports, like do I support SVE, and what is the maximum vector length can I support, and basic ARM architecture features that may be optional on the CPUs. And it also provides you a fundamental service to transition a particular page from a non-secure world into the realm world. So this is a basic of any most of the operations that we're going to see later. And it also provides ABIs to manage the life cycle of a VM, starting from the creation, allocating resources, and managing the resources, and tearing it down at the end of the execution. And the virtual machine CPUs, or the vCPUs, are represented by something called Realm Execution Context. It's just a fancy name for vCPU. And the RMM allows you to create virtual CPUs with an initial state populated. This will be measured so that the Realm can see how it was created. And RMM allows you to schedule these vCPUs under the control of the non-secure host. And the non-secure host can service some of the requests that comes out of the Realm, like handling the exits, data faults, and injecting interrupts. The interrupt management is completely under the non-secure side. The current versions of GIG doesn't understand the Realm world. The future versions of the GIG might solve this problem. And the host is in charge of managing the memory, adding memory and removing memory as it needed, and ensuring that the stage 2 translation, which translates the guest physical address to the actual physical address, is populated correctly. This is all monitored by the RMM so that it can provide the guarantees that the host is not playing tricks against us. And now coming to the services to the Realm. So the fundamental service to the Realm is ensuring that the host is not doing something seriously wrong. So how it does that by monitoring all the actions by the host. Primarily, it provides certain guarantees to the Realm on the IPA space. So RMM divides the IPA space into two halves. The lower half is called the protected half, where you have certain guarantees on the data that you can see there, and what happens if I access a particular page in there. There are certain guarantees there, and it can be controlled by the Realm, and provide permission for the host to do certain actions. And on the other side, the unprotected IPA space is completely unmonitored. Anything could happen, and the host is allowed to do anything it wants. And it also provides certain services to the Realm, like the fundamental is being what is the initial measurement where I was loaded. Like the host is in charge of loading the initial images, like kernel and guest firmware, and this gets measured by the RMM, and this can be extracted using the RSI call. It can also query the configuration of the VM, saying, oh, what is my IPA size, for example, or what was the algorithm that was used to measure my contents. And it also allows you to communicate with the host. So we have prevented the guest from talking to the host using the normal HVC calls. It has to be done explicitly via a new RSI called RSI host call. And also it allows you to manage the IPA state in the protected half, basically saying, oh, I expect this page to be RAM, and I can allow the host to provide a data page there. Please make sure that the guarantees are met. Right, and yeah, that's all I had to talk about. And it also allows you to add extendable measurements to certain slots. So there are up to 5 slots where the Realm can add measurements, and it can be extended. So looking at the ARM-CC architecture from the KVM point of view, in the normal case, you would be running the VM in the normal world, and you have a KVM struct which describes the virtual machine, which is linked to the vCPU structures. And on ARM64, we have a stage 2 page table that is also linked to the KVM and which manages the translations. You have the KVM UABI to talk to the KVM driver for the virtual machine. And more importantly, the guest interrupt is handled via a vGig interface that can virtualize the interrupt interface to the virtual machine. When you move into the Realm world, you are completely moving the virtual machine into the Realm world, and all the objects that are describing and keeping track of the realm is completely moved into the realm world. So basically, all these objects that you can see on this side, everything is in the realm world, and KVM has no access to these data. So we have a realm descriptor which describes your virtual machine, like the struct KVM. It keeps track of the stage 2 page tables and what was the parameters that I was created with, and it also keeps track of the the initial measurement data and all of the other things. And virtual CPUs are represented by realm execution codecs called REC, and they have their own state which saves and restores the register states, for example, and any outstanding requests issued by that particular vCPU. And the stage 2 is completely under the control of RMM. The KVM doesn't have view on what is populated in a page table. It can use the RMI ABI calls to manage all of these resources. And the host is allowed to inject virtual interrupts into the VM, and it can provide a list of registers called kick LR list registers. The RMM monitors all of this information and makes sure, yeah, I'm fine with this, I can inject these interrupts, and it populates the vkick interface. So yeah, that's how we do interrupts. Yeah, these are some of the things that we just talked about. All of this information is in the realm world. So we start with creating a realm using the RMI realm create command, and you can specify a set of parameters that describes certain properties of the realm, and this gets measured. One of the other things is the stage 2 root page tables, and that may not be measured because it could be different. Yeah, and you can create the vCPUs using the rec create. That also has some parameters, and you provide, every time you create an object, you provide where you're going to store the data. So you provide the granule which is in the realm world. And one of the important things about rec is that the storage required to store the state might be dynamic depending on the configuration. Like if you choose this SVA vector length of 2048, you need bigger pages. So how many pages do you need is exported via another RMA call, and it's based on the realm configuration, and you can pass additional storage at the realm creation using the aux pages. So that provides you for dynamically extending the size of each of the recs depending on the configuration. The stage 2 page tables are created using RTT create. RTT stands for realm translation tables. And it is reference counted for each of the mappings that they have, and it also holds some of the additional metadata that the RMM needs to know to ensure the guarantees. So there is a host state which says, oh, is there a granule assigned to this particular mapping or not? And there is a realm IPS state which is what is managed by the realm, saying that, oh, I want this to be RAM, or I'm fine this to be empty, and things like that. We'll come to that in the later. And the host is allowed to read individual translation entries using the RTT read entry call that provides you with all the information about host state as well as the realm IPS state, so that the host can take appropriate actions as needed. So let's go through the normal life cycle of a realm. So as usual, we have creating the realm, creating a VM, and you have on the bottom side you have the state defined by the RMM spec of the realm. The initial state is initial action from the host is to always create and with the parameters. So create an RD with the parameters, and you get some of the parameters to be specified there. As you can see that you have to configure the realm at the very first state of creating the RD. So that puts us in a state where we need to configure these parameters even before you create the vCPUs like we have now for the normal VMs. So we add a configure step in the realm lifecycle. This is only visible for the host and the VMM to configure the realm. Once we have that, you can load the initial memory images into the realm. As we said, the IPA has a state associated with it, and they need to be marked explicitly as RAM or empty. So any page that the realm wants to see as a part of the DRAM, it must be marked as RAM explicitly by the VMM in the beginning, and you can then create recs as needed. And there is one restriction on the in the order of creating the recs. It should be in the ascending order of MPADR. This lets the RMM, do the bookkeeping pretty much low cost. So that's the only reason there. Right, and once we load the initial images, you can mark it as active, and once you do the step, host loses control on most of the operations that it can do. At this point, you cannot create any more recs. You cannot load any known content into the realm's memory, and that's like a ceiling point. And the realm initial measurements will monitor all the actions from the create step until the active step, and that can be retrieved by the realm. So once you are in the active state, you can schedule the recs and service their exits, and RMM provides enough information for the host to service all of the exits. And at the end of it, you can destroy the realm using one of the RMA calls, or the realm can say that I'm going to shut myself using the PSCI system of call, and that would mark the realm as system off state, and further at which point you cannot schedule any of the recs. So a little bit about the vCPU scheduling. So you enter the realm vCPU using the rec enter call, and one of the parameters is a 4K page that is split into two halves. The top half is the rec entry, where the host can say, oh, these are the requests I have, like I want to trap if the guest does a wait for event or wait for interrupt, and or if it was servicing an exit with an MMIO emulation, it can say that I am servicing this MMIO emulation, so please take this value and populate into the vCPU register. And it also provides the interrupt state that is to be injected into the guest via this data structure. Yeah, and on exit, the bottom data structure is populated with all the information that it needs. Things like what was the exit reason, if there was a stage 2 fault, all the information required to populate it, and general purpose registers in case if it was a host call, which is passed via the arguments are passed via registers, and also the state of the kick v3 registers, and more importantly the timer state. So the host gets to know what was the timer configuration at the time of the exit, so that if you are putting this realm to be scheduled out, and if there is a timer set by the guest, the KVM can set up that timer, and when that happens, it can inject the interrupt back in and and put the realm back in. And there is also this specific request from the realm which says, I want to change my IPA state, and that's passed on to the host, and host can then take an action. So the RMA makes sure that host is not doing beyond, or host is not tampering with the request. It takes care of making sure that all the actions are according to the permissions from the realm. So let's talk more about the KVM support. Our goal was to keep the changes minimal, reuse whatever code we have, and keep it abstracted away. So we reuse most of the things that we have, like guest enter, exit handling code. VGIG is completely under the KVM, and for anything special that we need to handle, we add new constructs like, is this a realm? If so, do this step. Or if this vCPU is part of realm, do that other step. So, and we've tried to contain all the RMM interactions into separate abstractions, so that we can deal with potentially different versions of RMM in the future. Maybe we don't know. So it's all contained in different things. So the support for RMM is advertised using a new cap called ARM RME, and you can create. So you have to create a VM explicitly saying that I'm going to create a realm VM at the very beginning. So we are thinking of we have used the VM type bit, and we have we are allocating one field for realm, and could be for PKVM and things like that. So, and as you might remember, one of the major steps is we have to configure the realm parameters very early on. So we're using the KVM cap RME with the enable cap and specifying what are the operations that we need. This looks a bit overloading the abusing the enable cap. So we're planning to switch to VM attribute that Oliver recently added. Hopefully, that would make much more sense. And as you can see, some of the attributes that we are configuring at this step is linked to the vCPU. So we need to kind of find a nice way to move that to kind of VM level attributes so that it's much more easily integrated. Again, some of the other operations like loading the images into the realm is all controlled via the ARM RME. We'll be happy to hear if there is a generic solution that we can arrive at, given that all of us have certain needs to populate the images. And right now we have added a particular feature called vCPU rec for the vCPU so that we can control how the recs are created. So this is done by the VMM in the order of MPIDRs. Maybe we could move it into the KVM as a one-shot step to, okay, now go and create all the recs. So that's something we are thinking about. vCPU scheduling, it follows the common code. At the very end, before you call the hypervisor call, we just like, oh, is it a realm? Okay, if it's then go to the realm rec enter, and we make sure that all the GPRs and the vgig state is already synced into the rec entry, and set any other flags that you have to set to. Realm exits are handled separately, so that any realm specific exits are contained in the separate source files, and reuse all of the common exit codes like stage 2 aborts or wait for exit. Any of that falls back to the normal KVM exits. And also one of the other things is that we have to sync all the register states and the gig states so that the KVM can function normally without worrying about whether it's a normal VM or the realm VM. Memory management. So as you can see that the stage 2 is completely under the control of RMM. It is always with 4K pages. And it can support LPA2 and level 2 block mapping. So which can it's like having a 2 MB mapping at one shot. So and the KVM support we have added is dependent on the 4K pages, simply because it's too complicated to split a 64K page and keep track of where it went, and individual 4K chunks may be allocated in, and we can certainly improve that and add support for the other page sizes in the future. So KVM is supposed to donate RTT pages into the RMM. The RMM specs have been improved since beta 0 to efficiently handle most of the operations. And we don't need to use the read entry call that I mentioned earlier for most of the unmap operations or any of that. We use it only when there is something unexpected happening, like, oh, what went wrong? Then I can examine using RTT read entry. Been told that the restricted mem has been changed to guest mem. Sorry about that. So we are planning to integrate. We have a version that works with the guest memory, one version of the guest memory. So we are looking forward to getting that added to our stack once that's upstream. Right. So that's something we need to figure out. How do we load the initial image for the realm? I think this has been brought up in the past, but looks like we may have to do something on our own. And as usual, we service the runtime stage 2 aborts, and it's all common code. It's only that at the very last step, we don't call into the page table handling library, and we have our own way to do this. Yep, and at the end of the VM, so we tear down the RTTs and reclaim the memory. This has been quite fast nowadays. So current status is that the RMM spec is at EAC2. This was published last week. We posted an RFC series in January with the beta 0 versions. Spec has changed quite a bit in terms of memory management, and we are rebasing our series to support this. And we released the KVM and Linux guest support based on the 6.0. We also have some KVM unit tests for exercising the realm specific things, and we have added some new tests that we would that we have contributed. The prototype for virtual machine monitor is based on KVM tool. QEMU support was added by Jean Philippe in Linaro. That's also available. And has recently posted the guest firmware support that goes in that does specific operations to the realm, things like attestation and related stuff. So currently we are rebasing our work to the latest version of the spec, and hopefully we can post it in a couple of months. So one of the areas where we need feedback is about the user space ABI. I know most of the confidential computer architectures have certain requirements, and Realm ARM-CC has its own specific things, and we are keen to get feedback on the user space ABI to keep it cleaner and reusing as much as possible. So please feedback. And we plan to add the case self-test to the KVM to stress the KVM driver for now. This has been pending because of the UABHS. We didn't want to keep everything moving as the UABA moves. And the other work that is in progress is about the remote attestation flow, where a realm can talk to a remote entity. So yeah, that's something in progress, and this should be posted soon as well. And one of the areas that we are trying to generalize, come to a generic infrastructure is about how does a guest Linux kernel talk to the underlying secure thing and get the attestation measurement, and how do we expose that to the guest user space or applications that need it. Some of the future work, currently we are designing the ABIs for assigning trusted devices into the sure. So how do we assign devices to the realm? Basically right now none of the devices have access to the protected memory of the realm, so we are working on the spec changes to support PCI TDISC based device assignment. In this case, RMM is going to act as your trusted security manager. We are currently designing the low-level flow to allow the RMM to support this story and keep an generic way of discovering devices and managing this trusted devices. Another area that we are currently prototyping is partitioning the realm into different privilege levels. We call it planes. This would allow for you to run a virtual TPM in a more privileged level and than the higher OS, and provide the services, and that can be trusted. And then we have per realm memory encryption keys that's coming. Paging and live migration, it's not in the spec yet. We have not started working on it, but hopefully we'll get it someday. Right. So in the interest of time, I'm going to skip this. So if you have any questions, I'm happy to. Yeah, all right, okay. Yeah, sure, thank you.
Hello, hello, hello. I'm Mark. This is Oliver. Hello. He said hello. So this is I mean, we're both co-maintain KVM on ARM64. So unsurprisingly, we're really interested by Suzuki's talk about the CC architecture because we have our own take on that architecture. The title more or less sells it. So going to go very quickly through the first slide because you've been bored to death with confidential computing stuff. So this is what confidential computing is supposed to give you. Basically, you don't leak data. You can't infer data. Your data is safe. You can, software is able to verify that the platform has these properties. That's attestation, usually. And overall, what is not guaranteed is availability. You don't know whether you're going to be scheduled or not, but that's denial of service. In general, nobody cries too much about that. So ARM CCA is really made of a bunch of blocks. So you have the RME, Realm Management Extension, which Suzuki has detailed in great length. So it's a new security domain on the side. It's parallel to the two existing ones. You get some memory encryption. Recently, ARM has added per realm encryption. You get this fancy new third stage that basically is an additional permission check called granular permission protection check to enforce protection at a 4K basis. And it's exclusively managed by EL3, or now called root. And then you get the RMM, which is the Realm Management Monitor. And basically, it's some kind of proto-hypervisor, but not quite, specially designed to run confidential VM. And that coordinates with GPC to ensure isolation. So really, RME and RMM, that are the bits we're really keen on looking at. So this is basically another take on the drawings that Suzuki presented before. We should have merged these two presentations. So that's where we normally run them. So NS Hype is where KVM is normally, more or less merged with the operating system. And we have the VM on the side. At EL3, we have our firmware running, doing stuff. When you have secure mode on the side, well, you can have a secure hypervisor or secure partition manager, giving you some sort of trusted execution environment or secure partitions. The nice part is that secure has full control over non-secure, can happily spy your data. It's really good. And when you add the RMM and RME, then you can run realms. And the VM you were running in non-secure actually, it's not quite there. It's actually moved to the realm side. And EL3 has been keenly demoted to root. So it's still super privileged, but it's now its own world. What GPC ensures is that secure now cannot go and pick at the realm data. That's really the real innovation in this architecture. Well, for ARM. So what can RME do for you? Well, it gives you this split isolation model. You get GPC assigning, more or less assigning 4K physical blocks to a given security domain. And then you get your standard nested page tables to perform isolation within a realm mode. So when you run a VM in realm mode, we still have the same primitive to isolate them. It's your stage 2 page tables. And it's a split responsibility model. GPC, these tables are controlled by root, aka EL3. And the realm stage 2 controlled by the RMM running at realm EL2. So the software model is split as well. So we have some firmware running in root that is controlling this GPC. And then the RMM, as again Suzuki explained, is in charge of the guest state, the stage 2 page table management, handling of some, if not most traps, hypercalls from guests, and basically, well, anything that is related to CPU virtualization. The non-secure hypervisor that lives on the side, aka KVM, is providing memory, is in charge of vCPU scheduling, basically user space management, and for now, interrupt. So, so the RMM interacts with the the non-secure hypervisor, and you can create a RAM, provide memory, the payload, you can execute it, and then you can shoot it in the head and start another one. And all that is done using SMC calls to ER3 that are then relayed down to the RMM. For the guests, well, it's fairly similar. You get RAM Service Interface, RSI, it's a bad acronym, which allows guests to get an attestation report. As we've heard before, it's quite important. Manage the sharing of memory on the non-secure side. If you want to share back some memory, well, you would use one of these services. And also details like, allowing booting virtual CPUs. So we use PSA for that. And again, this is another set of secure calls, or maybe HGCs actually, handled by the RMM and potentially forwarded all the way back to the non-secure hypervisor. So it's quite nice. I mean, that's what we've done for PKVM. It's actually extremely similar, except that.
Maybe a few problems. So first and foremost, looking at the ecosystem, ARM's providing a reference implementation for the RMM. We can all go look it up and read it and everything, but there's no guarantee that the systems that we're actually running on are using anything that looks in any way similar to the reference RMM. Vendors are free to squeeze whatever they want into there, and it's deployed as system software. So it comes as a package with your firmware on your system. So there's no assurance around the correctness of it. We have no idea what bugs might lie in there. We have no idea when those bugs might be fixed. So it's really hard for us to make sense of whether or not we trust it in terms of KVM handing off its VMs to firmware. And to make matters worse, there's no way to even update it right now with the current specs. So you're pretty much stuck with whatever EL3 is given to you. The API around it, so there's two interfaces, right? The RSI and then the RMI, which is the realm management interface, KVM talking to the RMM. That's a rather baked API, and it's done mostly in the interest of a certain hypothetical hypervisor that we won't mention here. And the problem that we have with it is it doesn't build good primitives for doing virtualization. In fact, it actually builds in policy in terms of protection, and it doesn't give us the fundamental building blocks that we really care about. So we don't really get to play with the underlying hardware, and we're stuck talking through a firmware interface to whatever sits on the other side. So, and why is it that we have such a bad feeling about this being a firmware interface? Well, firmware has a pretty colorful history on ARM. It does on many platforms, but ARM in particular, we have our good friend TrustZone that has provided us a lot of interesting quirks and bugs, and of course, vendors wanting to cram DRM and all kinds of fun things on the secure side. Of course, other people have taken issue with this. Android is moving in a different direction. That's why PKVM exists, to move confidential workloads out of that super privileged space. A lot of the problems with this is like the SoC vendors, they fork it, they hack it up, and we wind up with just this massive ecosystem of a whole bunch of different varieties, and there's no reason to believe that the RMM would be any different. So the vendors are also trying to squeeze in a lot of value adds into a secure world, like the DRM, like I was mentioning, and it's really difficult for the kernel to adhere to something that's architectural at that point. And then to focus on the problem of doing updates of those firmware implementations, there have been bugs. It's hard to review that because we don't get to look at the source, and sometimes you wind up with interesting issues in your firmware, such as this Qualcomm one that Mark reminded me of, where your GPRs just get overwritten every once in a while, which is fun. So, we're going into this thing with the promise of write once, run everywhere, but really this is becoming write once and debug everywhere. So we don't want to be in a model of a ship and forget business for our RMM. It's very uncomfortable to build a hypervisor around that. So does this really make sense for us, and can we really trust our VMs to such an entity? And to make matters worse, all of this is built around the moral platitude of zero trust. The idea is that the VM doesn't trust the hypervisor at all. But I would say that trust is a two-way street. From the perspective of the VM, right, they don't trust KVM, but from the perspective of the non-secure hypervisor, I just see this giant blob to which I'm handing off my VMs. So very unnerving there. And the CCA ecosystem was built largely in the interest of a reference hypervisor that may or may not be independently verifiable. There's possibly not going to be any source code available for your hypervisor, but we know that's in no way true for KVM. All of our sins and mistakes are on full display, proudly. This fact has actually been used as the basis for another virtualization TCB, i.e. PKVM. And there's been some success with it. So it really prompts the question of why do we, by definition, lose trust in something that has a proven 10-year track record that's also innovating in the direction of providing confidential compute and taking the belief instead that firmware will do it better. So it's, again, this mythical common API through which all hypervisors can interact with hardware. It's supposed to be good for everyone, but in reality, it prevents any sort of optimization between the RMM and your non-secure hypervisor. So looking at PKVM, the interface between the PKVM low visor and the kernel is flexible. You can change it and optimize it as you see fit. But instead, with the RMM, you wind up with getting very, very common interfaces. It's very much dumbed down to coarse-grained interfaces, and again, a lot of policy cooked in there too. And then the question becomes, what do we do when there's actually a bug in the interface, in the spec? If this happened in PKVM, we could just go and respin the low visor and come up with a new hypercall interface to fix our problem. But now it's in the hands of firmware, and it's not clear that we could ever get a change implemented in the API in a quick manner, because again, it's dependent on all of our vendors doing the right thing. So then the question becomes, in KVM, should we just outright revoke support for these implementations? That's not very good. It doesn't feel like a good stance for the ecosystem, right? Because we want to be able to run on available hardware. But we may not even have a choice in it, because carrying all of the baggage of the hundreds of errata, if you will, of all these implementations would just really bog down KVM. So looking at some of the track record with KVM and PKVM, so like I had mentioned, having an inflexible API between your TCB and your non-secure hypervisor really didn't work, and it allows for flexibility and innovation, both in terms of new feature support, but also to respond to security issues and just bugs in general. It's also really important for performance. We can be very deliberate about what state exists where, be it on the RMM side, well, excuse me, on the PKVM side, in the kernel, or perhaps even shared between both. But now, since we're narrowing things down to a singular API, it's not going to allow for such diversity with the hardware. We're stuck with a software model, even though we really want to be getting to the underlying hardware. And a lot of the problems with innovation is not only is, so it's mostly focused around the reference hypervisor, but we don't get to build interesting things for KVM. And it also gets in the way of development for other ecosystems as well, because it's not the case that we're going to be just doing secure virtualization the entire time. We support non-secure. We have a wide variety of use cases that we want to support in KVM. Next slide. So as sort of a case study of like the performance issues that we brought up, so like having a more flexible API between the RMM and the hypervisor. One example of this is handling the GIC. At least in the current architecture, all of the GIC emulation lives on the non-secure side. I mean, yes, it's quite a massive pile of code, and understandably, you don't. Well, maybe there's one, maybe two of you who like it. Anyway, so all of the GIC emulation lives over on the non-secure side. So that means pretty much any time that we need to do any interrupt handling, It has to go all the way over to the non-secure world. And this is normal for physical interrupts, right? You don't want RMM to be handling unrelated physical interrupts in the system. But it really gets in the way of us optimizing virtual interrupt injection. And one example of that is the EL1 timer. The EL1 timer is directly programmable by the guest, but we get physical interrupts that come out into the non-secure hypervisor. But theoretically, we could come up with a model where perhaps some of that GIC emulation state is shared between the RMM and the non-secure hypervisor. If the RMM was able to introspect and look at the GIC state, it could perhaps determine to go ahead and inject a virtual interrupt that was targeted to the guest without even doing a full exit and context switch back into the non-secure world.
I'll take over. So what's interesting is that it seems to go into, at least on the ARM side, seems to go in the wrong direction. I mean, currently the direction of travel was that we're trying to, especially with the PKVM effort, and yeah, full disclosure, I've been involved with that, so I deeply care about it. We're trying to remove a lot of things from running in secure world, to bring that into VMs, and to break basically the correlation between being confidential and being privileged. And it is a change that we really need on Android, because people tend to run all kind of crazy stuff on the secure side. And we can do that without binary blobs that cannot be replaced. So there are some good properties. We can ensure that the payloads are confidential, but the hypervisor, everybody can run it, can hack it, hack it in sense, modify it, improve on it, and eventually ship it. And if you look at how the architecture works, it wouldn't be hard to take the non-secure EL2 side of PKVM, what people call the low visor, and move that as the RMM. The architecture actually lends itself really well to that sort of transformation. And we would have a fully self-contained, realm-capable hypervisor, where you can upgrade everything in lockstep, where you can have some degree of flexibility between non-secure and realm, and reap the performance that there are a lot of low-hanging fruits there that we could benefit from. But yet the CC architecture actively prevents this with the RMM. And it's really a bit annoying. CCA really reuses, and Oliver said abuse, the existing ecosystem. And it really begs the question, what do we do now when we get features that cannot be implemented with the current CCA architecture because of limitations of the RMM? Do we drop the feature on the floor? Or do we say that, no, well, sorry, RMM prevents us from doing so, so we're just, there'll be one loser in the end. It's not very good. I'm personally extremely concerned about the amount of platform-specific workarounds that we're inevitably going to have because of this model of forking existing firmware and vendors having all sorts of quirks on their platforms. These quirks are going to trickle down into KVM. From a maintenance perspective, it's not a good prospect. And frankly, it also means that we get a KVM implementation that becomes increasingly fragmented, siloed. So yeah, you can read. It's a rant, I agree, but enough ranting. That's the Italian speaking. So what do we need really? So if we want to make CCA really a first-class KVM implementation, well, we need an architected and secure way to deploy an RMM and at boot time, and an RMM that will be provided by the hypervisor itself. I mean, subject to all the possible restrictions you want, signing, secure boot exists for a reason, that should be part of it. So it has to be architected because we don't want, 36 or more different methods of doing so, and we want it to be verified, secure, attested, whatever. We're talking about attestation. We want an architectural way to measure that the RMM is actually what we think it is, and we want that to be independent of the RMM implementation. And we want to be able to leverage the secure boot infrastructures that exist. And there's a plural here because EFI and Android have clearly very different requirements. They work in a very different way, but we have also a very diverse ecosystem, and I don't think it should be the architecture to decide which ecosystem is more important than the other. And yeah, as we're now getting with QEMU some open source implementations, it'd be really good to have that quickly enough. So does it mean it's a wasted effort? Absolutely not. So the hardware architecture first is perfectly sensible. I mean, it maps really well onto the current principles of the architecture, with exception levels and stuff. We absolutely can see how to make it work. Provides the right primitives. Okay, we still have this nagging feeling about the GPC being handled by ER3 root, but there's no policy there normally. It should be be only behavior. Should be okay, hopefully. Even some of the RSI, so the RAM service interface is probably good enough. And I would love that to merge a bit with PKVM because they tend to overlap with different restrictions, but hey, that can be made to converge. Finally, even the RMM itself, I mean, it's open source. I haven't checked the license, but hopefully it's compatible with Linux itself. But it'd be good to be able to reuse some of the boilerplate code that exists there as a library and use it with other open source hypervisors. It's really the API we object to. So, had a quick look around. I know nothing about the other architectures, of course, but so what do they do? So for x86, it's sort of simpler because there are only 2 vendors, and they're very much in control of what's happening there. So the microcode helps. We don't have that luxury on ARM. But it still suffers from being quite inflexible. So it's in a way, it's a similar problem. But at least the upgrade path is really well defined. I've had a look at RISC-V, and at least for the stuff that has been posted on the list, it sort of looks like the RMM, at least Cove in the HS mode, where you have some firmware running in M mode and some other variants I didn't quite follow. You get an API, so I wasn't sure how it was called, but there was a CoV and CoV-H. Apparently CoV got renamed to CoV-G. Don't know why, no idea. Well, I think that's someone woke up. And for S390, I have no idea. Christian, you'll have to explain how that works. Oh, beer. Talking about that, almost. So here's a message to ARM. So CCA is really one of the major ARM-v9 features, and it really has the potential of redefining how workloads are isolated and made confidential on ARM. And making sure that the use of these functionalities, the use of the architecture really is not restricted. That's really essential. I mean, that's how the ARM architecture managed to get off the ground. And it has to be said, KVM has been really an enabler for ARM in the ecosystem. And we, especially in the data center. And we'd like to ensure that this trend continues, and we'd like to be able to carry on innovating in that field. So what we ask ARM is to give us the tools to basically meet this ambition. Oh, that's it. Thank you. There are questions.
Great. All right, hello everybody. Thanks for coming. My name is Jeremy Powell. And I work for AMD. And I'm here to introduce to you quickly our new feature called AMD Trusted I/O. So as a back history of where we were, and we spoke about this today a little bit, we've had two beginning states of our feature, which are secure encrypted virtualization and encrypted state. These two provide the confidentiality features of our confidential compute solution, and they are present in EPYC, first generation and second generation. Now, coming to our third generation, we introduced secure nested paging. Secure nested paging is the point where we introduce the integrity and confidentiality, and with that, we've been able to talk about having the hypervisor being drawn out of the trust boundary of a guest. So now we have the question of what do we do with I/O devices. At this point in EPYC third generation, devices are outside of the trust boundary of a guest. Now we're trying to bring that into it. So S&P's goals were to draw the hypervisor out of the trust boundary. We do this by through a data structure in memory called the RMP. The RMP provides a per 4K granular page set of security attributes for each page, and it's deeply rooted in our address translation features. So both the IOMMU and the CPU MMU are using this RMP data structure to say whether or not a page is assigned to a guest or a page can be accessed by the hypervisor. Another major portion of S&P is our AMD Secure Processor, the ASP. You may have heard it called the PSP. It's the same thing. The ASP is involved in the general orchestration of lifecycle of an S&P guest, and it provides a secure interface to the guests as well as to the hypervisor for control. And so we have some upstream support for guest kernels, and we're working on the host side. So here's the state of things today. When a guest wants to interact with an untrusted device, the untrusted device can DMA into shared memory. When the untrusted device touches shared memory, the IOMMU treats it as if it's hypervisor access. And so that way we can have safe but usable access to devices. However, the RMP will check to make sure that that when the device accesses it, it's not accessing private memory. Same thing goes for the MMIO. Whenever a guest accesses MMIO, it has to be done through a shared memory address. If the guest were to try to p-validate, which means to accept an MMIO range into its private address space, that would be rejected. That's not a possible thing in current S&P guests. So one of the downsides of drawing devices out of the trust boundary of a guest is you have to bounce buffer. So instead of having a untrusted device talk directly to private memory, we have to bring the untrusted device's DMA into a bounce buffer, and then the guest has to burn its own CPU cycles to copy that memory from shared memory to private memory. So when we introduce Trusted I/O for SCV, we have to say, okay, well, we're going to relax the security policy to some degree to allow a device to touch private memory. But we need to provide control to allow the guest to say, I trust this device. So at the big picture, the untrusted device hands a attestation blob or blobs to the guest, and the guest examines that as part of its attestation flow, And then it says, I trust this device. And it tells the AMD security processor, which does a bunch of SoC magic, to say, okay, this is a trusted device, and it can now touch guest private memory. So now we have MMIO. The guest can now, through our TIO interfaces, allow for MMIO to be mapped into private memory, and the RMP will allow that. Similarly, the IOMMU will allow DMA to private memory as long as the ASP has provided, has marked that device as trusted for that particular guest. So kind of stepping down one level into the architecture, we have a bunch of setup and pieces and parts that bring this all together. There is a control channel between the ASP and the SoC and our devices, our trusted endpoints, called SPDM. SPDM provides a means in which to send specific messages to the device to ask it to enter certain secure states and to set up the next point here, IDE, which is integrity and data encryption. So IDE is it can be a link level, or it can be a point-to-point. What we're talking about here is point-to-point, and it's going to encrypt all traffic, encrypt and authenticate all traffic from the IDE controller in our root complex all the way to the port of the trusted endpoint. The AMD security processor has to go through a few steps on behalf of the guest to ensure that not only the page mapping that we have, page mapping protections that we have for SMP in general for DRAM pages, where the hypervisor is not allowed to do page swapping attacks. We also want to make sure that the MMIO ranges are the actual device that the guest expects, and we're talking to the offset in those ranges that the guest expects. So the AMD security processor will do some work on behalf of the guest to determine that, and then it will tell the RMP, it'll write it into the page of that MMIO offset, that this MMIO range is accepted, and it'll provide, it'll unlock that MMIO range for the guest. A new thing we've added to the architecture is this concept, this data structure called a secure device table. If you're familiar with our IOMMU architecture today, we have a device table. This is in addition to the device table. It's a secure device table that contains the per device security attributes associated with the guest. So today, the device table contains things like guest paging mode. We've moved that out into our secure device table, and now this is where the IMMU will look to find information about how to tag the accesses of DMA from the device to the guest's private memory. Excuse me. The ASP also has to program this because the SDT is inaccessible to the hypervisor or the guest. And the ASP will retrieve information about paging modes or other things that the guest provides, the guest needs to provide, like where the page tables are, in order to put it in there for the guest. And so then the IOMU will tag those accesses appropriately. So now this SDT represents sort of a, rather than always considering it hypervisor access, now it can access it as if it's a guest. So in order for this all to work, we have to work closely with the devices. Devices need to provide some isolation between guest workloads. They need to provide a way to freeze and attest to the state of the device. And so we have this PCI standard that was ratified last year called TDISP, and TDISP will places the requirements of having a state machine for each TDI. TDIs are the PCI parlance for an assignable interface that have these requirements. Place a state machine that controls the configuration of the interface. It places the requirement for IDE, and it has a whole bunch of transaction level rules that control how packets flow on that PCI fabric. Also through the requirement of SPDM, they have brought in concepts of authentication and attestation through SPDM channel. And the mapping between AMD's technology and the spec is the TSM and the TDA spec is the ASP, and the TVM is the SMP guest. The state machine basically provides a way to tell the device to stop letting configuration that might change the security configuration of the device until the guest has allowed, or excuse me, until the guest has attested to that or retrieved the attestation information of that device. So we don't want the configuration to change after the guest is asked for the configuration and has accepted it. The locked state and the run state are the security states. The unlocked state is legacy behavior. So when a guest does attestation, it will ask the ASP to transition the device or the interface to the lock state, and then it will ask, hey, give me all your attestation information. The guest will accept it, and then the TDI will be transitioned to the run state, and that's when DMA and IMMIO can happen. In some cases, the device could choose that, could say, I've reached an error that is insecure, and I need to nuke all the guest data inside of me. So it can transition its interface to the error state, and it can basically sit there until it's purged all of that guest private data. So the guest TDI lifecycle is kind of married together. We're really talking about how do we bind TDIs to guests. First, the hypervisor will want to set up that device connection. It will ask the ASP to set the device connection up and build that SPDM channel, build the IDE channel between the hardware and the device. And then it will do TDI operations to bind the device or device's interface to the guest. So this is where we say in this SoC, we program the SCT. We say this device interface is bound specifically to a guest, and we don't allow TDI to be bound to multiple guests at a time, so we're enforcing that invariant. Once the TDI is bound, the guest will retrieve the attestation reports and go through that validation flow, and then it will ask the ASP, hey, now that I understand what this device is configured, I want you to program the RMP and allow that private memory MMIO access. And then following that, it'll unlock DMA by programming the IMU, the STTE. There are a number of open questions, I think, in this flow. The question of whether or not devices should be enumerated as TDIs, already locked and run, or if the guest should be able to access, or sorry, request that the TDI is bound to that guest actively. I think a lot of that has to do with the specific guest and hypervisor architectures. So one of the things that we'd like to talk about today in the BOF is, or one of the BOFs is to discuss how this all merges together. Taking one further step down, we have a number of firmware commands that help this process through. We have some commands to manage the device's lifecycle. We have some commands that manage the TDI lifecycle. And we have some commands or guest messages that allow the guest to operate on the device from within the guest. So if you're familiar with S&P, we have a thing called a guest context page. This is a buffer in memory that the hypervisor donates to the to the ASP, and the ASP stores a bunch of context information about that guest for the purposes of S&P. So in this way, we have kind of extended that concept to devices and TDIs. So we'll have a context page for a device that'll contain a bunch of stuff like the S&P state, SPDM state, and then we'll have a TDI context that will describe the information about what we expect the state of the TDI to be. So this is largely, these commands highlighted here are largely memory management commands, so we're being able to allocate and reclaim them. We have two commands that allow to connect and disconnect. These commands are building that SPDM channel and IDE streams between the ASP and the devices. And so we are generating the IDE keys, we're pushing them into the devices, and we're programming internal SoC configuration to allow that. So this is where we ask the device. So now we have this SPDM connection to the device, and we want to say, lock your configuration, don't change anymore, and we want to prepare the device to be attested to and to be used. So the TDI bind command takes both a device identity and a guest identity, and it connects those two inside of our SoC. It says, okay, now we know that this guest is bound to a TDI, and we transition the TDI to the locked state and then to the run state. This was the idea of moving straight through past locked was considered to be a simplifying assumption for the API. The run state basically prevents DMA and MMIO, which is redundant in our architecture. We can prevent that on the host side. So we transition to the run state for simplification. And then we have an unbind command. The unbind command does basically the opposite of what you'd expect. It's important to think about the unbind command also as the way to recover from errors. So if there's an error condition, either a device was ripped out of the box, or a device gets reset, or the guest falls on its face, there are a number of different error conditions that we need to handle. The unbind command is the way to escape those, and so we basically allow that to almost always succeed, so that we will just clean everything up. So attestation, which is a fun topic, we have three basic objects for attestation. We have the device's manufacturer certificate chain. We have an attestation report that's defined by SPDM and to a large degree by the device itself. And then we have an interface report, which is defined by the TDIS specification that describes the interface configuration, largely the MMIO ranges. We have some commands to retrieve those, and the hypervisor will retrieve them and hand them to the guest. And the guest will use this TDI info request to say, ASP, what was the last message that you retrieved? Give me the digest of it. So that way the guest can make sure that the hypervisor hasn't changed the objects in transit. So once the guest has done its authentication, and I kind of put a big asterisk there because there's a lot to be figured out with how to appropriately attest a device, the guest will then go through MMIO validation. So the guest has a range ID that it wants to write to map in, and it has a GPA. And it says to the ASP, I want you to validate this MMIO range. The ASP will then use its values that it knows about the interface and the MMIO ranges from the interface report, which contain the SPAs of the bars. It will do some lookups in our RMP table to figure out whether or not those pages were mapped to the guest, whether they were mapped appropriately to the GPA, and will ultimately confirm that the MMIO range is positioned in space on top of the bars in a way that the guest is expecting it to be set. And then once that's set up, once that's checked by the ASP, the SCV firmware will then write the RMP entry to an appropriate way for the guest to be able to access that memory in private address space. The SCTE write command writes this 512-bit STT entry and for the interface, and this is where the guest is going to provide its guest paging mode, the pointers to its page tables. The ASP will provide some of the entries some of the values in that entry. This is where we bind the ACID value. So this is how we tell the IMMU this is the guest this device should access the memory with. And then once it sets the V bit, the validated bit for the SCTE, then the IMMU can start accessing memory for DMA for that device. When we have guest paging enabled, there will be a need to use the hardware accelerated VIMU. This is primarily necessary for a guest to have a trusted path to the IMMU so that it can invalidate IOTLBs and the IMMU TLB. So SCVTIO, in conclusion, is intended to bring the devices into the trust boundary of guests. It also prevents traffic snooping and tampering using the IDE stream, and it can produce possible performance improvements by removing the bounce buffering requirement for access for DMA. If you want to learn more, we have information about in our white paper, and then there's also a technical preview of our ABI that you can find out what the specification for each of these commands are. And then this afternoon, we intend to have a BOF of some kind to answer some of the following questions, like what does the device model look like? Should devices change? Should they be enlightened for TDISP? How does the attestation flow work? Like who is processing the attestation reports? Is it the drivers? Is there remote attestation flows? Should we support all of that and provide all the hooks and flows necessary there? So with that, that's my talk. So are there any questions? Yeah.
So this relates to one of your earlier slides. I understand that IDE protects PCIe traffic from snooping and tampering and stuff like that.
Mm-hmm.
But assume that DMA transfer is landing from the device in guest memory. Does some kind of re-encryption happen there? Because when the guest code is running, it will try to read the data that the device just produced.
That's right.
So is it integrated somehow into the memory controller? Because I figure that the encryption used for IDE might differ from the encryption you use for encrypting and decrypting guest memory.
Yeah, that's exactly right. Yeah. So when DMA comes through the IDE stream, it's encrypted at the device and decrypted at our root port, and then it flows to the IMMU, hits our data fabric, and goes out to our UMC, or our memory controller. And the memory controller, it's the same logic for SEP. You have keys, and it all gets tagged with the right guest identification.
So it goes through that. From one of the earliest SEV specifications, I recall an expression calling it a high performance EAS engine or something like that. So that I'm not sure if that's valid, if my memory serves right, but it goes through the same channel.
That's right. It goes through the same encryption engine that a guest would go through to access memory.
Thank you.
Yep. Sure.
It seems to me that if you're trusting, or you don't need to trust the device very far. What I think the best power out of this is the ability to say this device can DMA to just these specified areas because I've got VIO-MMU. And if it's a NIC, then you're using, you know, TLS or whatever. And
nice. Yeah, so your point is, like, you know, we can use the IMMU to limit the GPA space that the device can actually touch. Is that right?
Right. So you get rid of the bounce buffering, but you don't have to trust the device because there's many devices. If you're distrusting your cloud provider, it's probably the cloud provider's NIC in the first place, and so on. So I think that it'd be better if you don't talk about it only as trust the device, but also as a way to improve device performance without having to trust it.
So you already have, before TIO, the ability to manage the space of memory that the device can touch through guest paging. But in that case, you know, we have the prevention of accessing shared memory. But at the same time, if you care about that, or you're in a conventional guest, then you can do that. We're not affecting that here. We're allowing that same control to exist here as well. So it's a sort of a layered approach on that security.
So when you have reached our state, is there any way to recover from that state? Your slide said not reconfigurable, but is it possible to reset the device and we go through attestation from within the guest or not?
You have to. So once the device enters the error state, TDIS requires the error state to, requires the TDI to go to the unlocked state, which is essentially the case where you have to go through that whole binding flow, you have to go through the attestation flow. So the recovery from that perspective is re-enumerating, rebinding, and re-attestation.
So my understanding is the PCI host bridge, you expect it to still be emulated, right?
Yes, that's true, right? So the information about where the device lives in GPA space, like the MMIO ranges, all that's going to be provided by the hypervisor, and it's going to be untrusted. And that's why we go through the ASP to say, you know, the hypervisor told me this device lives at the GPA 5000 or whatever. Then can you confirm that for me? And that's what the ASP is doing.
And so is there going to be like a mix of trusted and untrusted devices, like on the same host bridge?
That's possible, yes. Yes, that's possible.
Okay.
I have one question, because I saw like in the TIO paper, it said like, you know, the MMO mapping will not be accepted by the p-valid anymore, so the paper said it might accept through the GHCP core, I think. So I was wondering, like, you know, when you are going to destroy a VM, so who would release those RMP entries? Does the hypervisor need to do that, or like in the TIO unbanned, you know, the PSP firmware will release all of them?
So one of the commands is to do the MMIO validation. That's a command to the ASP, and that's going to get flowed through the GHCP protocol. That command is essentially p-validate, so you can both set and unset the validated bit for that MMIO range. And then, you know, the hypervisor can still reclaim pages forcibly, if it needed to, of all the MMIO ranges that have been assigned to that guest, just like it would for DRAM.
Okay, thanks.
Okay.
Okay, my question is, what is the scheme for firmware updates on the card? Is this bringing the card in error state then? You have to go through the loop, or is it forbidden to do firmware updates?
That's a great question.
Or do you rely on firmware certification and chain of trust?
Yeah, that's a great question. I mean, ultimately, what it broadens to, you know, how does a guest owner trust a device fundamentally? And a lot of that is device specific. There are bits in the TDIS spec that say, no, you can't update firmware while this TDI is in the run state. And so that can be a control to allow a guest to not have to worry about that. But if you do need to update firmware, and at the, you know, that would affect the guest, and it would be driven by the host updating that firmware. I think protocols need to be built in software to figure out what that looks like, and it may be device specific. But that's a really interesting question to answer. Okay, I think that's it. Thank you, guys.
Cool. So mic is on, or? Okay. So hi, and welcome to my talk about the Coconut SVSM and ingest parallelizer in Rust. I'm Jörg Rödel and I work for SUSE. And first of all, the question, why do we need an SVSM? For that, let's have a look into the confidential computing threat model again. With the confidential computing threat model, usually all emulated hardware becomes untrusted because it runs in the hypervisor. The hypervisor usually emulates all your peripheral devices, so those become untrusted. Any input from those devices becomes untrusted. And this usually includes all peripheral devices. Also APICs, network cards, disk controllers, everything. Even IRQ injection, TPMs, which is an important part. When all of these devices become untrusted, the OS needs to be hardened against malicious input so that the OS cannot be tricked to release any secret that you have in your confidential VM to the hypervisor by exploiting bugs in device drivers. Another approach is which is also common in some confidential computing environments, is to actually move hypervisor functionality like device emulations into the guest context, into the trusted guest context of the confidential virtual machine. So, as I said, either the OS needs to be hardened, but for some device drivers this is not enough because some devices carry security sensitive state. So there's no way to securely emulate them in the hypervisor even with a perfectly secure device driver. An example is the TPM. where the state must not be visible to the hypervisor because the TPM state carries secrets like, for example, disk keys or other secrets. Must not be visible to the hypervisor, otherwise it can just decrypt your disk and get your secrets from there, and all your nice memory encryption is useless. To actually emulate a TPM within guest context, we need another hardware feature which was already mentioned today. This is the VM privilege levels. This is needed because it's not enough to hide device state from the hypervisor. We also need to hide security-sensitive device state from the operating system. Otherwise, it's not secure. Otherwise, some exploit in the operating system could steal the secrets from the device and make the TPM insecure. And this is where the SVSM comes into the picture, because what the SVSM is basically an emulation layer for devices inside the confidential guest context, making use of the privilege level feature. Today I want to talk about the Coconut SVSM, which is our SVSM implementation. Let's start with some history, because that has been on the mailing list. So our SVSM started in early 2022, actually in parallel to the Linux SVSM. I think when we both started, we weren't aware of each other, but later we became aware. And we talked to each other. We talked to AMD about the design, but we never reached a point where it actually made sense to get the projects together. So we have the situation we have today with two SVSM implementations. Linux SVSM was at a point where it could be released or where it could be published in August last year, and our SVSM reached that point a little bit later, mid-March this year, so over half a year later. Yeah, so that's the reason why there are now two SVSM implementations. What is Coconut in a nutshell? It's an SVSM implementation written in Rust, just like the Linux SVSM. It currently has around 11,500 lines of code. And that is actually a feature of the Coconut SVSM. It focuses on isolation within the SVSM. It shares actually parts with the Linux SVSM code base, or with the Linux SVSM stack, in that it uses its OVMF and Linux kernel both for host and guest changes. So we rely on those to run the SVSM. Only the pure SVSM implementation is separate. Well, and the QEMU patches to actually launch the SVSM. And it's currently running on AMD SCV SNP, so it's making use of privilege levels, which is an SCV SNP feature. So it currently runs there. The project is on GitHub. You can clone it, you can file issues, you can participate in the development. It's all there. Just look at this URL, and yeah. There's also an installation guide which tells you how to set it up, and if you want to try it out today. So what features do we already have in the Coconut SVSM? We support the SVSM core protocol, which is a base for every SVSM implementation, because in SCV SNP some operations that are needed to manage a confidential guest are VMPL0 only, so they are only allowed in the highest VM privilege level. Operations like page validation, that can only happen in the highest privilege level. Same with making the memory actually available to lower VMPLs. This can only happen in higher privileged VMPLs. And the same is with CPU creation and deletion, that also can only happen in VMPL0. So this is what the SVSM core protocol provides as services to an operating system running on top of it. And the operating system needs adoption to not do these operations with the instructions used on VMPL0, but to actually make a call to the SVSM for these operations. Yeah. The isolation features of the Coconut SVSM As I said, it was designed with a strong focus on isolation. It has per CPU page tables, which has some nice properties because we can map stuff at fixed addresses like IST stacks or the per CPU data, and we don't need the GS register, which comes in handy later because we don't need swap.js, for example. We have work in progress, and that is probably the most important design decision we made in the very beginning of the project. We have work in progress to enable executing ELF binaries as modules at CPL3, so isolated from the core SVSM code. The idea is that these modules will provide additional services to the OS. So it's called a service module, right? So the services should run at a lower processor privilege level and isolated from the core SVSM. One of the services is, of course, a TPM, but many more services are possible to emulate with this design and architecture. At some point, we also need an IPC mechanism when you have multiple modules running in parallel so that they can talk to each other. One use case, for example, is attestation. The SVSM attestation protocol has a feature where the OS can request attestation reports from all services running in the SVSM, and for that, an attestation service would need to ask all other modules to get attestation data, and that would need IPC. So, but we don't have a design for that yet. It's something we know we need, but it's on the to-do list. Some more on SVSM modules. As I said, they allow a nice separation between SVSM code and third-party modules. Here a little bit more on the reason why I made this decision. Very early when I thought about a possible SVSM design, I looked into what it would take to emulate a TPM in an SVSM. And I looked into different TPM code bases, and they were all written in C. And these code bases also pulled in crypto libraries, which are also all written in C. And when you want to write an SVSM in Rust, at least that is my opinion, and you run your TPM emulation in C alongside your Rust code in kernel mode, then there's no reason to use Rust in the first place because your memory safety guarantees that Rust gives you are somehow, going away with that. So very early I made the decision to run modules at CPL3, so we can have a VTPM that's entirely written in C with a crypto library entirely written in C, and have it isolated from the core Rust code base. So this is work in progress, as I already said. This needs some boilerplate code like task management and scheduling. We already started with that, but we hope to finish it sometime this year. Finish is a bold word. Get something running. It's certainly work in progress to get it ready. We need task switching. We need task memory management. And we need a Cisco interface. That's probably the thing that's going to evolve over time, depending on the needs. So this is a plan that we look what modules actually need, and then we find a way to implement this in a secure way in the Cisco interface. There's a GitHub issue for this feature, which can be tracked. Where you can see what progress we make. We already implemented some parts of it, but yeah, lots of other stuff is still work in progress. So use cases for modules I already mentioned. The TPM for runtime, which is needed for secure runtime attestation within the guest. But there are also possible modules like a UEFI variable store was mentioned. With that, we could hide UEFI variables from the OS, which would make secure boot in a confidential VM secure again. We can have an attestation service running as a module. We can have even other device emulations running as a module. So I think with the module design, we are well set for everything that will be possible with VMPLs, which is, I think, a lot more than just running a TPM. We can maybe even put the core protocol into a module. That's something to be discussed. yeah. What other features does the Coconut SVSM has? It boots in 32-bit protected mode using a two-stage bootloader. More on that later. It has a global memory allocator using buddy and slap algorithms, which is cool because with that we can use basically everything in the Rust alloc library, which is smart pointers, strings, vectors, everything that allocates memory. So all of that can be used in the SVSM code base. We have an ELF loader that will be needed for ELF loading anyway for running modules, but we already use it to load the actual SVSM kernel into memory. We have console support with switchable backends. Currently we only print to the serial console, but we want to have it in the log buffer at some point and not print it to the console because everything you print out is visible to the hypervisor and a potential security problem. So the plan is that we have a log buffer and make the log buffer requestable by the operating system. So you can see the SVSM logs from within the guest, but not from the hypervisor. You have some debug features, like serial console support, I just mentioned that. We can collect and print backtraces. So this code is separate. We can collect it and print it at a later point. We use it to print backtraces on Panic, which is quite good for debugging. And the fact that we can collect it and print them later is also helpful for log debugging. We haven't implemented this yet, but once we run again into deadlocks, then it will become very useful for that too. And we have an optional GDB stub, so you can enable it on your make invocation, and then you can attach your GDB to a dev PTS device, which is routed via serial into the guest, and talks to the GDB stub there, and then you can basically do debugging of the SVSM. As I said, this feature is optional. It's of course only for development, so, but I think it's very helpful. So this is what we support today, what the SVSM supports today. So we can't run modules at CPR3 yet, but that's the highest priority item right now. Beyond that, what are our future directions or plans or what we have in mind? None of this is set now, but it's basically some ideas I want to present here. So first idea is about the SVSM boot process, which as of today is not optimal, I think, because it requires quite some non-standard QEMU changes or SVSM-specific QEMU changes, let's say it so. So how the SVSM currently boots is it is presented to the guest as a third option ROM after OVMF and OVMF variables. There's a third one for the SVSM, and QEMU parses metadata of this option ROM and sees it's an SVSM. Then changes the initial launch state basically to not launch in real mode but in 32-bit protected mode, and sets a new launch IP and basically starts the guest from a different IP than the standard one. And then the SVSM will start with its two-stage loader. The stage 1 loader runs directly from ROM. It's completely written in assembly. What it's basically doing is taking the stage 2 loader, which is in the same option ROM, relocated to the first 640K, actually to 64K. So 64K is the base address for the stage 2 loader, and also for the stack, because the stack grows downwards. So stage 2 also has a stack. Then it jumps to stage 2. Stage 2 will do some evaluation of its environment, like querying the memory map. We'll find a location for the SVSM kernel to run at. And when it found a location, then it will take the SVSM kernel, relocate it to a memory region, and basically jump to the SVSM kernel, and the SVSM kernel launches and does its setup, and finally gets to booting the OS VMPL. So this is not optimal, as I said, because it uses a non-standard initial CPU state, and it requires actually a lot of SVSM-specific QEMU changes, which I don't quite like. So one option to get out of this is bundle the firmware into the SVSM binary and let and present the SVSM at option room 0, which would allow it to start at the default reset state again, so at real mode, 16 bytes below 4 gigabyte instruction pointer, and just boot up from there. And then the SVSM basically takes care of putting OVMF or the BIOS into the right position in memory and launch it. So this is one option. We actually have a pull request which implements that. But there's another option which I come to like more, which is to load the initial VM state from a single file. So there are currently efforts going on of defining a file format which describes the initial state of a confidential guest. So it describes the initial memory layout, it describes the initial register states, it describes locations for other info you can put into the guest, like the MADT ACPI table, other ACPI tables, a guest memory map, and all of that. The file format even supports multiple platforms, so you can have one file and use it to launch confidential VMs on different platforms. So this is currently in the works, not by us, but by someone else. And what I actually like about this idea is that it would provide a standard interface for launching a confidential VM across hypervisors, because it provides an hypervisor-independent way for the SVSM to be launched. So otherwise, the SVSM would need hypervisor-specific code to request the memory map, to request the API IDs and everything. And with using such a standardized file format, the SVSM basically knows where to find the data, how the data is formatted, and every hypervisor basically provides the data to the confidential guest, and the SVSM doesn't need much special code for that. Now this is option 2, which I like more, I have to say. As I said, it works as a cross-hypervisor interface. And yeah, the final decision also needs to take other architectures into account. We've seen today that other confidential computing architectures are also working on features similar to privilege levels. So yeah, I think it makes sense to take those into account too. Another thing which we need and which we have not fully designed yet is a persistency layer. So the SVSM needs to be, or modules in the SVSM need to be able to load and store data or make data persistent. For example, that the TPM can store its state, or that you can provide an initial TPM state. Same for UEFI variables. That storage needs to be encrypted and integrity protected, of course, and it needs to be only accessible by the SVSM. The big question is how the hypervisor SVSM interface, what it looks like. Is it a block, basically block device presented to the SVSM, or is it some file object based interface like firmware config or whatever? Yeah, it's not decided yet, but that's something we need to work on. Another feature which I really like to see in the SVSM is the SVSM doing interrupt proxying for SDV SNP. Because there is currently support for restricted injection implemented for Linux, but there are quite some objections, let's say it so, which I expected. So I think it's unlikely to land in the Linux kernel soon. So why not let the SVSM take care of securely injecting interrupts into the guest? That would mean that the SVSM actually takes the IRQs from the untrusted hypervisor via restricted injection, and then forwards them to the guest via alternate injection, to the operating system via alternate injection. That requires at least a partial APIC emulation within the guest, because the SVSM needs to know TPR and EOI and IRR states, or needs to keep track of that to know when an IRQ can be injected. So that's to be discussed, how to actually implement that, whether implementing that via a new protocol, or whether we rely on the Reflect VC feature. It's still under discussion. and if anyone has input, we can discuss that. Next thing I think which would be great is to let the SVSM keep track of the validation bitmap, so which memory is validated and which is not, which parts of memory are shared and which are private. And possibly move the checks for those into the SVSM2, which would remove quite some or which would offload some logic from Linux to the SVSM. The benefit is that the SVSM has a lifetime of the virtual machine, while the OS can be rebooted. It can be kexec, there can be kdump, and on all those events, when you reboot the operating system, when you do a kdump, you need to forward your validation information to the new kernel in some way to stay secure, because you need to know which memory is validated and which is not. Right, and having that data in the SVSM would basically solve that problem. So that is something which I think would be great to have. And the vision or ultimate goal, I would say, of the SVSM is to become a full paravisor, to run mostly unenlightened operating systems, which needs reflect VC support. So VC exceptions would no longer be handled in the operating system, but would be forwarded to the SVSM, and the SVSM handles those. This would also allow running more device emulations as modules, like for example a full APIC emulation. We can have, it would probably also require VTOM support, because the OS which is Windows, which would be the customer of this mode, relies on VTOM, the virtual top of memory support. But all of this is not easy to achieve, and I think it will require a more complex syscore interface to get all of this implemented and running. So I think that's enough for today. Thank you for your attention, and if you have any input, questions, objections, anything, let me know. We can talk now or in the BOF, which is at 3:45. There's a Coconut SVSM BOF. You're all invited to participate there, and where we can discuss further technical stuff there, or now as you want.
So from 1 to 10, how feasible do you think it could be to reuse the SVSM, VMPL ideas outside confidential computing as a replacement for what we do right now with SMM?
Can I answer that one? Of course. The only thing we do in SMM is UEFI secure with variables, really. That's the only sensible thing. The emulation really is nested. Oh yeah, Paulo was saying I was also doing emulation in there. Emulation really was just a crutch that you could just as well do using nested virt, which is probably much more superior. Plus, we're going to have a BOF on how to do this better. The real answer to SMM and getting rid of SMM is to move the UEFI variable store into KMU. It just does not make sense to have an SMM at all.
I think so. For the code base itself to run in a non-confidential environment, I think is not that difficult. We need to make it aware that it may not run under SCV SNP, which it currently expects. So. More questions, input, ideas, objections?
I think I got maybe 20% of what you said, so forgive me if it doesn't make a lot of sense. You're talking about moving the emulation of TPM inside of some sort of guest context, right? Devices like TPM have state, which sometimes need to be in shared storage, so you can power cycle the VM in other hosts or things. How do you see the connection of a device that has persistent state inside of the secure context with the persistent storage?
So yeah, the persistency problem is basically should be solved by the persistency layer. So that layer should survive the VM destruction and new setup and new launch. The question which we have not solved yet is how to get the key for that storage into the SVSM. So that is a problem we still need to solve. But
Okay.
when we solve that, then we basically have almost secure persistent state within the SVSM. I say almost because one problem I'm not sure yet how to solve it is how to prevent replay attacks of the persistent storage. So that the hypervisor just presents an older version of the persistent storage to the SVSM. The SVSM has no way to detect that.
Okay. I imagine it's the same problem for UF5 vars, right?
Right, right.
Okay.
So you mentioned that one of your objectives was to run C implementations of the TPM at VMPL3, and that one of the things they were bringing were crypto libraries. And I think there were some discussions about trying to provide some kind of mechanism akin to, what the Linux kernel does, to expose shared code so that it could be used by VMPL3. Can you expand a bit on that?
I haven't thought much about it. I've read the ideas, but we have to see how big the problem really is, right? How much memory a crypto implementation really takes, and whether it makes sense to have something complex like a dynamic loader and to actually share, to basically have something similar to shared libraries. It's not something I anticipate for the first supports, but we can evaluate and see if it makes sense.
Yeah, so if I recall correctly, it was not so much about shared libraries as exposing VDSO style stuff to. So yeah, that is a part of shared libraries.
That's also, VDSO is basically also a shared library, right? So, but yeah. So what you're saying is that the SVSM basically carries the crypto library with itself and maps it into each guest space. Yeah, we can think about that. That could work, yeah. But
the question being whether you trust the crypto stuff to be at VMPL3 or whether you want to edit it yourself.
Well, it's everything that runs in the SVSM, including the modules, is measured at boot time. But I don't want the C crypto code at least to run at CPL0. So I want that to run at CPL3. So it's say that again?
And it would run at CPL3.
Right.
Okay, thank you.
Okay. Yes, I am. Okay. My name is Claudio. I work at IBM, and I'm here to present this VTPM, Virtual Trusted Platform module. We've been working for confidential VMs, and we call it Zero Trust because it has to follow the trust model of a confidential virtual machine where we cannot trust the hypervisor. This is the outline of the presentation. So I'll give you an introduction and walk you through how of the problem we are trying to solve. Give you some background on attestation, and also and then discuss about the VTPM we are working on. Discuss some design topics and also the architecture. If we have some time, I'll give you a demo and leave some time at the end for questions. Okay. So when an application have sensitive data, we need to protect the sensitive data. The application needs to protect the sensitive data end to end. It means at rest, in transit, while it's in the network, and also in use, while it's in memory. For the first two, at rest and in transit, there are solutions that relies on basically cryptography. But for in use, we need to rely not only on software, but also in hardware. And that's where this trusted execution environment technologies try to address, try to solve, protect data while it's in use, which it's basically create an hardware isolated environment where you can put your application there and run it. TE technologies, they can be applied in different levels. We can apply them in a process level, and more recently there are technologies, TE technologies, that allow us to apply them in a virtual machine level. So we can create an enclave and add your virtual machine inside that enclave and run your virtual machine. When we say that, when we have a virtual machine inside of an enclave, we usually say that we have a confidential virtual machine. And these are the technologies that supports that. Currently, SEV, SNP, for example, actually, Intel DDX, ARM CCA. And as I mentioned, all these technologies, they protect the VM data while it's in use from unauthorized access. And in this case, we are more concerned about hypervisor and also cloud service providers. Confidential virtual machine has been explored in multiple use cases, such as cloud, I/O, and multi-party computation. When it comes to consumption model, when we launch a confidential virtual machine, usually first customers want to attest if that virtual machine, if that confidential virtual machine is really exactly what you expect it to be. It's in the state you want it to be. And it has not been tampered with. But then it brings a question: how do we attest a CVM then, a confidential virtual machine? And the idea is similar to the one we have in the host. We use measured boot with attestation tools. And measure boots, we need to measure not only the boot, but also runtime. And for confidential virtual machines, we can request a VM launch measurement, which covers basically the initial state of the VM. But then it's not enough if you want to do attestation, because we need to measure every subsequent module that is loaded after this initial state. And there are solutions up to the guest OS. There are solutions proposed already, but they are not standard, and they also rely on untrusted entities. In the last KVM Forum last year, Tobin and Dov started discussing that, how we could have a more standard way of attesting a confidential virtual machine. And we believe that using the trusted platform module is a good way of doing that, because the TPM is an industry standard for attestation, and it also already has a TPM tooling, a rich TPM tooling that we could reuse. And additionally, we could use the integrity measurement architecture, which is a more advanced technique for runtime attestation. And that was our motivation then to develop a zero trust VTPM for confidential virtual machines. And our target platform is the AMD SCV SNP. Okay, it's about attestation. So let's quickly go through TPM-based attestation. There is this TPM. The TPM is a trusted platform module. So it's a chip. And it provides these platform configuration registers. And the way that these registers work for attestation is that as we boot a system, we take measurements of every event that could change the state of the virtual machine. And then we record these measurements in the platform registers. And there you can see the SHA-1 bank. It has 24 registers. There are other banks as well. I'm using the SHA-1 because it has small hashes. But the way that we record these hashes, these measurements in the TPM PCR is through a PCR extend operation. The interesting thing about the PCR extend operation is that it doesn't destroy the current value. It builds on top of it. So if you do a PCR extend, you need to provide a digest, and then the TPM will take your digest, read the current PCR value, concatenate both, and take a hash of this new string, and use it as the new PCR value. With this idea, what we see in the PCR values is a value, but it represents a ordered event of a series of events. In other words, an event log. And that's the idea of attestation. We can just get these PCR values and compare with the values that we expect them to be. And if they do not match these values, we can go through an event log. We validate this event log, but we can go through an event log and find out where exactly it's deviating from what you expect. And there are several tools there are some tools that could be used for attestation. One of them is the Keylime. It's important to understand that these attestation tools, the first thing that they will do is check if they validate your TPM to see if it's an authentic TPM. And then it will do the attestation as you request later at runtime. Okay, now that we understand about attestation, for the Zero Trust TPM, there are some key points that we need to discuss to solve. And I'm going through each of these points now, but basically they are: where should we run the VTPM? How can we prove that the VTPM is authentic? And also discuss about the state of the VTPM, injection or ejection. Okay, the first question is, where should we run then the VTPM? The VTPM it doesn't run in a physical TPM. So we don't have the protection of the hardware, the VTPM hardware, to protect the state of the VTPM, the TPM data. In our case, a VTPM is a software. It doesn't run in the TPM chip. We use the Microsoft TPM 2.0 reference. And since it doesn't run in the TPM chip, we must protect the VTPM state. We must protect the TPM data from unauthorized access, especially the hypervisor, but also from the guest OS. Based on that, there are some, initially we thought about 3 options. We could run the VTPM in the host, but it's not a good, it doesn't seem to be a good idea because the host kernel would have access to the VTPM data, to the VTPM memory. So another option would be to run it in a confidential VM. This seems to be a more generic approach, a more generic solution that would be easier to implement in other architectures. But on the other hand, it also brings in some complexity in terms of orchestration, because the VTPM would be running in a separate confidential virtual machine, different from the virtual machine that we are running, and every command we send, we would need to send to this separate confidential virtual machine, and also there is the probe, and the VTPM would need to be available at the beginning of the boot, at early boot. It would complicate also the orchestration. Based on that, we think that the best option for us is to run the VTPM in the confidential virtual machine that we want to attest. But still, where exactly inside that confidential virtual machine that we want to run the VTPM? And we run it in the SVSM, the Secure VM Service Module. We do that because it's the first module that runs in SCV-SNP guests. And with that, the VTPM would be available for subsequent modules to take measurements and start using the VTPM. And also, because the SVSM is used to provide runtime privilege service to the guest. And if you look at this SVSM specification, the VTPM is one potential candidate for privileged service candidate to provide services for the other components. And also, we run it in the SVSM because the SVSM leverage the VM privilege level feature from the SNP platform, which basically allow us to take the address space of the guest and divide it into multiple levels, VMPL 0 to VMPL 4, where the VMPL 0 is the most privileged one. And since we run the VTPM here in the SVSM, the SVSM runs in VMPL 0, and this way we protect the VTPM data from the other components, subsequent components, OVMF and guest kernel. Okay, but if we run the VTPM here in the SVSM, there is a change that we need to make in the VTPM drivers. Because the VTPM drivers would not talk anymore to the TPM chip. It would talk to the SVSM VTPM. In other words, the SVSM needs to provide runtime services for the other modules, for the other software components, and also the VTPM driver would need to send the VTPM commands not to the TPM chip. It would need to send them to the SVSM VTPM. And we worked with the community to define this VTPM protocol. You can see that in the SVSM spec 0.62, Tom, which is back there, and he sent this spec to the Linux Coco mailing list. Currently, there are two SVSM implementations, the AMD Linux SVSM and the Coconut. We are working with both of them. We started pushing pushing patches to the Linux SVSM, and now we started working with Coconut. The other big question is about authenticity. When we talk about the TPM authenticity, we need to talk about the physical TPM too. How can we prove that a physical TPM is authentic? Physical TPMs has this endorsement key, which is a TPM identity. Each physical TPM has its own identity. And when it's created, when the EK, the endorsement key is created, the EK, the private part of the EK never leaves the TPM. We also have this EK cert, EK certificate. which basically is a certificate of authenticity for the EK. And the TPM manufacturer ships a TPM with these two, the EK and also the EK cert. The EK cert is how it, the EK certificate, it binds that EK that was generated to a TPM manufacturer, because the manufacturer will sign a certificate that contains that EK pub. And that's how it's done in the physical TPM, but how can we do that, a similar idea, for the SVSM VTPM? It's easy to create the EK. The EK is not a problem. We can just issue a command to the VTPM and say, okay, create for me a primary key. But the first thing that we have to do before creating the EK, we need to make sure that we have a good entropy source at the beginning of the boot, because the EKs would be created at early boot, so we need to make sure that the entropy source to create the EK is good. And for that, we changed the rand function to call the platform RD rand assembly instruction. And since we are using the Microsoft TPM 2.0, it depends on OpenSSL, so we have to have an OpenSSL. The real question is, who would sign, who would give us a certificate of authenticity for the EK we just created, that the SVSM just created? We know we don't have the TPM anymore, the TPM chip, a hardware, to certify that for us. We don't have a TPM manufacturer. But we do have the platform, the AMD platform. And we can call the AMD secure processor to issue a certificate of authenticity for the EK using the S&P attestation report. When we request attestation report, basically the AMD service secure processor, it gives us back a signed attestation report that changes back to the AMD key, root key. And that's how we can also chain the have a certificate of authenticity for the EK we just created, because when we request an attestation report, it takes two arguments. We can pass two arguments. One of them is 64 bytes, and these 64 bytes will be also in the attestation report. We use that 64 bytes to pass we pass the SHA-512 hash of the EK pub in this report data, these 64 bytes. And then the AMD service secure processor would give us a certificate with this EK pub hash inside of it. But still, there is a question. How do we make sure that this attestation report was created by the SVSM? How can we ensure that the EK was created by the SVSM and not by any other software component or even other SVSM in other GAST? Well, the attestation report also takes a VMPL level. So we request a VMPL 0 attestation report. And since only the SVSM runs in VMPL 0, it's the only one that can request an attestation report for VMPL 0. Because the request is encrypted with a key that is available only in VMPL 0. This key is the VMPCK 0. And that way, we can prove the authenticity of the EK we generate in the SVSM. It would be signed by, it would be an attestation report that would be chained back to the AMD root key. And also, all attestation report requests that we do here anywhere in the GAST, it needs to be encrypted because this request goes through the hypervisor. And the hypervisor, it would need to know, to decrypt this message, it would need to know a key that is available only for the guest and the AMD secure processor. And that's how we protect this request from the hypervisor. It's a standard protocol available in the SNP platform. And lastly, I want to talk about the ephemeral state. Currently, on every boot, we create the EK, and then we request a VMPL0 port to bind the EK we just generated in the SVSM to the AMD hardware through the attestation report. And then we save this attestation, this VMPL0 attestation report in the TPM NVRAM, so that later at runtime we can just any attestation tool can go to this TPM NVRAM index we saved and verify the authenticity of the TPM. And with that, we have an ephemeral state for the SVSM VTPM. We know that there are some use cases that requires persistent state, but we think that there are many advantages by having an ephemeral state, and it would be enough for doing attestation. Some of the advantages is this ephemeral approach. It has a simple design, and it's already good enough for having runtime attestation, a TPM-based runtime attestation. And one thing that is very important is that we don't need to eject or inject state, which is complicated in this case from the perspective that we don't need to protect any state when we eject the VTPM state at a certain point in time when we want to destroy that guest. And then when we boot the guest again, we need to get that state, inject that state into the guest. That brings some complexity to the threat model, because we will need to secure the state at rest as well, and also at runtime, while it's in use. And with the ephemeral state, we don't need to do an early attestation for the VM launch measurement. Because if we want to inject the state, first we need to make sure that before injecting the state at runtime, that while the SVSM is booting, first we need to make sure, we need to attest if that launch measurement is really what we expect. And that brings complication to early boot, because we will need to have more code to do that. And with ephemeral state, we can postpone it to runtime. And also, there is no need to secure, I've already talked about that. We don't need to secure the TPM state at rest and in transit. State injection requires more code and also orchestration at early boot. For example, we may need to have some network stack at early boot. And in general, the attack surface when we have a ephemeral state is much smaller compared to persistent state. Another thing is migration from the perspective of the TPM would be easier, because we don't have states to migrate to another guest. The disadvantage is that we may have limited use cases. It works for runtime attestation, but we know that there are some cases, for example, full disk encryption, that requires persistent state. For that case, we can use, we can enable full disk encryption by having an intermediate storage key. We could generate an create an intermediate storage key, and then do some sealing of the disk encryption key to that intermediate key, and have that key in the, for example, loaded in the initRD. The process is a little bit complicated to do that, but it's possible. Okay, and this would be the SVSM VTPM architecture. We have a proof of concept. You can go to that link and look, check, clone it and try. But that proof of concept, it uses Wolf SSL and also uses the CRB. Currently, we are not using that anymore. We tested this proof of concept with Keylime, the attestation tool. And we are contributing the SVSM VTPM to SVSM open source projects. So here inside the SVSM, we have the core and where we have most of our contributions, because we need to integrate the VTPM, the Microsoft TPM, and also integrate libcrypto and a small libc, I would say. It's only the libc, the runtime part of the libc, and it's based on Muscle. And both the core and also the VTPM depends on crypto functions, crypto support. That's why we have OpenSSL there. Currently, everything is running inside the SVSM, the AMD SVSM, and it's running in VMPL 0, CPL 0. We have, for those that want to join the discussion today in the BOF, we can discuss that, how we can better isolate all these components inside the SVSM, but using the Coconut SVSM. Okay, so how we are in terms of time? Huh? 2 minutes. Okay. Okay. So now I'm going to do a simple demo, and I want to show that when the SVSM is booting, it says that the VMPL 0 attestation report in the TPM and VRAM, and I want to validate that attestation report to see if it's authentic. Basically, we have to go through 3 steps. The first one is check if the signature is okay. We need to go to the AMD website and download the key that we expect this attestation report to be signed with, and then validate the signature. And once the attestation report is valid, we can check the content of the attestation report. We need to make sure that those 64 bytes that we use for the hash of the kpub matches with the hash of the kpub that is available in the TPM, VTPM. And we also need to make sure that this attestation report was generated in VMPL 0. In other words, it was generated by the SVSM. Okay. Following the same idea, this is a zero trust demo, okay? Here, as I mentioned, I'm booting the SVSM that I compiled from the proof of concept code. And for that code, we use a CRB driver, TPM CRB driver. We do not use that anymore. And it uses Wolf SSL. Currently, we are using OpenSSL. Okay, we are booting the guest. And here you can see that OVMF is already able to found the virtual TPM and start recording measurements to the VTPM. Okay, the guest booted. The first thing I want to show is the PCR read. So we can see that the VTPM was found, the guest OS found the VTPM, and it was populated during the boot, all the PCR values. And also, the step you just saw is the EKPub. We have to get the EKPub the same way that the Keylime expects. Keylime expects the EKPub in the TSS format. And this is the EKPub, 316 bytes. And welcome to my debug image. There's a lot of debugging messages because that's the only thing we can do when we are debugging a confidential virtual machine, because it's encrypted. The memory of the guest is encrypted. And then we get the attestation report also by reading the TPM and copy the attestation report and the EKPub to the host, simulating a remote attestation, but it's not remote. And here we run, I run this validate SVSM VTPM Python script that basically follow those steps that I mentioned, which is basically check the signature, download the key from the MD's website, check the signature, and then check the content of the guest. Okay, and this ends my presentation. And for conclusions, the SVSM, we have the SVSM VTPM is protected from the guest. The VTPM data is protected from access coming from the guest OS and host OS. The EK is unique because it's generated randomly and it's authentic. The EKPub is authentic because we have the attestation report. And we have this ephemeral, which is a simple design, but it's enough for TPM-based attestation. And that's it. We are contributing it to the open source projects. We have time for questions? No? Okay. Thank you.